seemingly not very loud. Oh, now I'm very loud. Hi, folks. Big warm welcome to SPLASH'23. We have some great papers in this session, and so I'm going to turn it over to Cyrus as the session chair in just a second. But just a couple notes. So the goal for today is that when presenting papers, ideally authors maybe 22 minutes, somewhere between your range. But then what we'd like to do is have small group discussions, so maybe like 4 minutes at tables, which is why we're sitting at tables, to discuss the paper amongst yourselves. And then we'll do kind of open Q&A for the last couple minutes, and we'll keep time on that. After lunch, we'll do a couple just-in-time introductions. One of the great things about the Splashy community is that it's a lot of educators, and so if you want to get to know each other, we'll do kind of quick-fire, rapid, hi, I'm Molly, this is what I'm interested in, come find me at the coffee break and chat. And so to facilitate that, we have some slides here. I'll put that up later as well. And that's kind of my intro. You'll hear more from me later, and I'll turn it over to the start of the session.
So actually maybe, since there are only a few folks at some of these tables, if we could coordinate on filling the tables, that might be helpful. And if people are coming in late, if people could just quietly kind of point them to sit. Okay, so the first talk of the session will be Teaching Programming with Graphics, Pitfalls and Solutions by Luca Chiodini.
Thanks for the introduction. Hi, everyone. I'm Luca, and I'm about to present Teaching Programming with Graphics, Pitfalls and a Solution. Now, bootstrapping every talk is always a difficult part. Let's see if I can get your help in this. Here's a claim for you to assess. Maybe you or one of your colleagues are using exercises with graphics, say, as opposed to just exercises with numbers or strings when teaching an introductory programming course. What are some quick pros and cons you can identify about that? Sure.
More interesting for our students?
More interesting. Others? Oh, requires some complicated background that not everybody might have. Other claims? This seems mostly like it. I think I had an easy time guessing you. On one hand, some people describe it as, oh, this is like fun. It's attractive. It's more motivating for students. And on the other hand, some people say, well, but it's a little bit too hard. Maybe it's too complicated. Or maybe it's even distracting from the main purpose. I'm teaching kind of introductory programming. I don't want to teach like geometrical concepts. So it seems that we have like two teams here. One is a little bit about the complexity, and one is about the engagement. And then a lot of people, when they teach like an introductory programming course, especially if it's like in high school, they say, well, I don't really want people to become programmers, as we have been just discussing, but maybe I want to teach like some computational thinking skills, whatever that means exactly. But one of the skills that is often cited in computational thinking is like, oh, I want them to be able to do problem decomposition. I want them to identify some problems and solve them. So we have three teams. And so when we teach introductory programming with graphics, we would like to have like these three goals associated with these three teams. One is that we have complexity, and we would like to manage this complexity. Another one is that we have engagement, and we want to have, sure, students engaged, but we want to direct this engagement towards meaningful concepts. We want them to learn programming in the end. And then when it's about problem decomposition, we would like to have a library, an approach that allows us to have like a clean problem decomposition. So we have these three goals: manageable complexity, meaningful engagement, and clean problem decomposition. Now, the first part of this talk is about identifying some pitfalls that we identified in existing libraries to do programming with graphics that have to do with these goals and that it might hinder the reach of these goals. And to show you those, I'm going to use a basic example. This house, this is a very famous example, using some existing libraries. But before showing the code, I want to make an important premise. This is about teaching complete novices, and it's about teaching them programming. So the actual goal in the end is to have like some basic essential programming concepts. Now here's the first snippet of code. I'm going to use Python, very popular language nowadays for introductory programming, and one of the many libraries, this one is called CS1 Graphics, that is supposed to be used to teach introductory programming using graphics. So here is how it would go to create that house I just showed you. We would first create an empty canvas, then we would create, say, a square for the floor, then we position the floor appropriately at certain coordinates, we add the floor to the paper, and then we need to do the same for the roof. We don't have a function directly to create the triangle, but we can create a generic polygon, and we can specify the points of the vertices of this polygon. And we have our roof, we can add the roof to the paper, and this is how the code looks like. Now, if you think of introducing this piece of code to complete beginners, you might think that you would have some difficulty here in explaining what are all the language features that are used in this code. Well, sure, we have like some functions that we need to use, but this goes beyond functions. Here we have like object instantiation, and then we not only have functions, but we have objects, so we have method invocations. And then we even have like a variadic constructor here for polygon that can take in a variable number of parameters. So we have like a lot of language features, and this is the first pitfalls that many libraries incur into. Now, for something different, let's say that we want to create a second floor for our house. This is how we might extend the code. This is the same code as before, and I'm just going to add these 3 lines at the end. I'm going to create the second floor, I'm going to position it appropriately, and I'm going to add it to the canvas. Now, very quick show of hands. Who believes the actual result of this code is the one on the left? 1, 2. Who believes it's the one on the right? A couple. A lot of shy people. That's fine. So the surprising thing, or maybe not so surprising, is that it's the actual result is the one on the left. Because what's going on here is that against the fairly typical novice intuition, this is not creating another floor object, but it's merely creating 2 variables that refer to the same object. And so here we have mutation going on, and this is actually quite complicated to introduce novice programmers to. And so mutability is this second pitfall that we identified that might hinder reaching the goal of manageable complexity. Now, onto the meaningful engagement. So here we have the student who's unable to create or struggles to create the desired house. Now, here is what might happen. The student goes into the documentation of the library, looks a little bit at what's available, and then they discover that there is actually a class that's called image that takes in a file name. Oh, that's an amazing discovery for the student. This is what's going to happen. The student is going to go on Google, it's going to type house, it's going to look a little bit, maybe this one, maybe not exactly, let's see. Okay, this one looks great. This is a great house. I'm just going to save this one on my desktop, and then I'm going to solve my problem just by creating an empty canvas and adding it the desired image. And here we have it, our amazing house. And that looks much better than the ones I had just programmed before. So even though external images have their purpose in introductory programming, actually they might hinder the engagement. And this is why we're considering the ability to load external images a pitfall. For something different, here is how we might solve the house problem using Pirate and its image library. We might be able to create the floor using the square function. We might be able to create the roof using the triangle function. And finally, we can combine them together to create our house. Now, this code is very nice, gets to the point, very terse. Now, why exactly is it that we are able to solve our problem so tersely? Well, the reason is the Pirate API, the library, the image library of Pirate, actually has a large number of primitives. These are kind of all the possible shapes that one can create directly, and they are all one function call away. And then we have like a large way to compose this, a large number of functions that are able to compose these images. And so what happens is that students, instead of actually defining their own abstractions, say the one that creates an equilateral triangle, can just spend time into looking into the documentation and find the right function. And that distracts a little bit from the goal, that is teaching programming concepts and not teaching a specific library that maybe they're not going to use again after this introductory programming course. So having a rich API is the second one of our pitfalls that go under the meaningful engagement goal. Finally, let's get to this third, a little bit more weird goal, perhaps. This, we would like to have like this clean problem decomposition. Consider this house and consider a simple variation of this house. The previous one had like the roof at height 87. This one has the roof at height 120. This is the same code as before. Could you help me in changing this code so that we get to the right picture? What do I need to change? Some help? Yeah, there are like 287. Maybe this is not the best code, but this is how it was written. We need to change this 287 to 120. Is that it? Oh, I need to change the move somewhere. There is a move there to 137 for the y coordinate that needs to be turned into 170, which is a little bit of a weird number, which results like from 50, the center of the square, plus 120. And this is really weird. I mean, besides that this code is maybe not exactly how you would have written it in the first place, this is not how we would like this, this problem to be solved. I mean, we only wanted to change our roof. This is a more general description of this. We have our problem, we need to draw the house, and we divided our problem into two subproblems, drawing the floor and drawing the roof. And then we came up with solutions, with programs for those two subproblems, the floor and the roof. And finally, we were able to combine the solution into a house. And so we have like these two subproblems, and the key here is that we would like to solve them independently. But what happens in the previous code is that the floor, the position of the floor depends on the canvas origin. The coordinates at which it's positioned, those are global coordinates. And the same goes for the roof. It depends on the same canvas origin. And so here we have like two subproblems that depend on a shared global value. And that's why global coordinates are considered a pitfall to achieve clean problem decomposition. Now, this problem was recognized a very long time ago already from Papert when they introduced turtle geometry. Because turtle geometry, if you think a little bit about it, provides a local perspective on drawing. You're embodying the turtle, and then you're instructing the turtle for certain commands. And so you have here your house. Now, the original implementation for turtle was in Logo. But nowadays, Turtle is available in almost any programming language. There is a library. So I'm still going to use Python for clarity. And I'm just going to solve the first subproblem here. We need to create the yellow square. I'm going to change the pen color of the turtle. Here, for brevity, I'm just going to do the outline. And then I'm going to use some repetition construct, and I'm going to move the turtle forward, and then I'm going to turn it right by 90 degrees. And by following exactly what the Logo manual does, I'm going to package this piece of code into a function or a procedure, if you wish. And then imagine that we have solved the roof problem in the same way. So we have two functions, one that draws the floor and one that draws the roof. And then I'm going to call these two functions to be able to draw the house. But this is what's going to happen. The turtle is going to draw first the square, and then it's not turning in the right way, and it's going to draw the roof not in the way we want. And so what happens here is that we need to have some glue code here, we need to have an instruction such as turn left by 60 degrees to adjust this code and make it produce the image we want. And what's the interesting fact here? Well, solving the floor problem actually depends on and even changes, mutates the turtle's state. And similarly, solving the roof subproblem depends on and changes the turtle's state. And that's why we can't have this clean problem decomposition. And so here is our second pitfall, the turtle state. Now, this problem, again, was recognized long before. This is, I think, goes back all the way to Henderson, 1982. He introduced functional geometry, and it's kind of this approach that is more taken into the functional programming community to treat like images as values. And it's also the approach that it's embodied in the image library for Pirate. And so there we only have like combinators, and there is no notion of a global coordinate system. We only have a local coordinate system, which students discover when they look at all the combinators I was showing you before, and they discover that there is one, or actually many, but one specifically, like put image, that, okay, takes two parameters, an image and a background, and places the image on the background so that its center is located at a certain coordinate with respect to the bottom left of the background. And this is good for solving certain kinds of problems, but it's easily abused by students and also by some teachers when they teach in Pirate. This is an example that comes from the Bootstrap hour of code. This is the final task of the hour of code, and this is what the student is being told to do. Look, your task as a programmer is to change the coordinates of these subproblems, and maybe if you want, add a little bit more. But the problem here is that every subproblem, sure, there is no global coordinate system, but there is a local one, and we are abusing the local one as a global one, because every subproblem now depends on the background's origin. And that's why, even though they are useful for certain graphics, local coordinates can also hinder clean problem decomposition. So that's about the pitfalls. Now, what do we do as a solution? Well, the solution is very easy. On one hand, you just don't do any of this. What's the problem is now what you can still do. And so the rest of my talk is convincing that you can still do something meaningful even without doing any of that. And we embody this approach in a Python library that we are dubbing Pytamero. And here is how solving the house problem would look like in Python using Pytamero. Now, unlike the previous snippets, this is a complete Python program, meaning it's complete with imports and output. So this is, in full honesty, what you need to do to program with Pytamero. You need to import certain names from the library. Then you create the floor, very similarly to how you're doing it in Pirate. You create the roof. Notice that here you don't have an equilateral triangle function because the API is very slim. It doesn't offer you a specific equilateral triangle function. There is only a generic triangle, and students then can define their own abstractions once they have seen repeated code over and over. And you can still combine the two subproblems using a combinator. And finally, you can show the house. And this is everything that the students need to know in order to being able to create a house with Pytamero. Now, our approach pushes and encourages to decompose a problem visually. Here's what I mean by that. This is an example taking the emblem of the International Red Cross. We see naturally that we have a red cross onto a white field. And then we also see that the red cross is made by a horizontal arm and a vertical arm. And if we want, we can even say that the vertical arm is an horizontal arm rotated by 90 degrees. And so this is actually fairly easy. Now, it might be even too easy, and you should be complaining, okay, that was a trivial example. That's not fair. What about more challenging graphics? So now I'm just going to take it a little bit one step further by showing you this heart. How we can program this heart? Well, first of all, it might look easier if we rotate this heart by 45 degrees. And now, what are we going to do? We're going to use, again, some Pytamero primitives here. We can combine them and rotate using everything we have seen so far. And now we need to introduce a new concept that every graphic has a pinhole, a designated position for pinning, that is then used to combine this graphic with other graphics. And so what's actually happening is that these graphics have a pinning position. There is a function in Pytamero to repin a certain graphic into a different location, and we control the locations in which it's possible to pin. And we can then use the generic compose function to compose the two graphics, aligning their pinning position. And finally, we rotate the heart to achieve our problem. The neat thing is that by leveraging this composition pattern over and over and over, students can actually create stuff that is relevant and they like a lot. Pac-Man maze is a common example. Games are often very popular. And here they can create like a full-blown maze just by composing the specific tiles. This is very common to tile-based boards. And the specific tiles, in turn, are composed out of Pytamero primitives. We can actually create meaningful graphics as well, not necessarily just games. One of them is warming stripe visualization. That's actually something interesting. Or if you're doing, let's say, a science class, you might be interested in having your students, instead of just looking at a periodic table of elements, create their own periodic table of elements. Or say you might want to use a graphic that is culturally relevant somehow. Here is, for example, the Swiss railway clock. This is culturally relevant for Swiss, but it's also somehow known worldwide. And there are actually many more examples. A touch or a point that touches upon something we have been just discussing in the keynote, Pytamero attends to the idea that students, especially younger students, might want to program in their own language, and it attends to this point only at the level at which Pytamero situates, meaning a library. And so we have been fully localizing the API, and that means not only the function names, but also the parameters, the error messages that we give, and the documentation. And here is how the same house example would look, for example, in Italian. It's quite cool. There is more in the paper. We have some more example of how students can create their own data visualization as opposed to just using a library that visualizes the data. Here the idea is, well, why can't you compose the graphics out of primitives? And so you're learning about data visualization, but you're also learning about programming at the same time. There is a discussion on how combinators offer multiple ways to decompose a program by the very nature in which they are written. There are some beautiful connections to algebra that unfortunately I don't have time to explain right now. And there is also discussion on how we are gradually introducing types, even for Python, which is not like standard practice, and how we are connecting that to the documentation. Now, some limitation, very briefly. I've presented some pitfalls at the beginning. It's mandatory for me to say that I understand that different contexts call for different goals, and so not everything I said is applicable to every context. And the second major limitation is that we have so far been using Pytamero in teacher training courses, in a first-year university course, and in high schools, but we only have like anecdotal evidence of the fact that it's working to counter some of these pitfalls, and we are working on studying its effectiveness with a more rigorous evaluation. So I'm inviting you to check you out. We have a platform for this library. On the platform, you obviously find the documentation of the library and how to install. That's just a pip install Pytamero away. But you can actually do something even more interesting. You can program with Pytamero directly in your browser. The website offers more than 150 activities with Pytamero, and there are also some guided curricula that sequence the activities for you. And I'm very happy to report that some of these activities and curricula have been created and are currently used by some Swiss high school teachers. And that's it for what I wanted to say about teaching programming with graphics, some pitfalls and a solution. Thanks.
All right, great talk. So we have 4 minutes, so chat about the talk, and then we'll have a few minutes for questions about after that. Yes. Yeah.
Sorry, just to repeat kind of how we're doing questions in /E. So we're going to do small group discussions at tables. So if you're not at a table with a small group, maybe join a small group. So we're going to have those conversations for 4 minutes, and then we'll open up
Yeah.
for
To a few questions for the speaker, and then as we get towards the end of the question period, we'll have the next speaker set up as well. Okay, so just raise your hand if you have a question. All right, right there.
So I was looking at your pirate example. I think you were a little bit unfair because that's more about function composition than anything else, right?
Okay. What do you mean by function composition?
That you that code is breaking it down, like you're suggesting, but it's putting it all into one global expression instead of breaking it down nicely inside the code like you do in separate expressions.
Right. I assume you mean this piece of code then. Let's see. Maybe we can get the...
Yes.
You mean this? Oh, but I didn't write this one.
I know.
Took this one from Bootstrap, which is the leading curriculum that uses...
Yeah, I understand. But that's basically decomposition, right?
Right.
So...
But, I mean, you see that some of these sub-problems might be merged into in a hierarchical structure. I mean, this is about building a snowman. And so you have certain things...
I completely agree with you. This is not the type of code I would encourage, right?
Okay.
But my more important point was about aligning the pinholes. So it seems to me like you didn't talk about place image, which is based on using a coordinate system, which I think beginning students learn in high school. They know what X and Y coordinates are, and I think that might be easier than figuring out how to align the pinholes for them.
No, there is definitely, I mean, I'm not blaming coordinate systems altogether. And I know that there are actually some very great uses for coordinate systems. Say, for example, if you're modeling any kind of like real world game or some kind of graphics that is about like physics simulations maybe or games. And therefore like you have your problem that inherently uses a coordinate system. And then by all means, that's great. You want to position stuff at a certain coordinate because that's where the stuff is supposed to be. And I wouldn't use pinning for that. The problem that we're describing here is that these coordinates, especially very early on, can be abused. And students tend then to write, this is actually from experience, in TAing courses that use HTTP, how to design programs, as an approach, and seeing the students that write in their final projects code that has like numeric constants all over the place, and they haven't really gotten the gist of like composing stuff where more appropriate combinators would be available, and only using coordinates for places where coordinates are really required, saying I'm modeling something for physics, and I need to place something at a certain position, X and Y.
I agree. Take a look at animated problem solving. It'll take it a step further than how to design programs.
All right.
Yep.
Okay, let's do one more question while the next speaker gets set up.
So our table was discussing a lot about not using numbers at all, like none at all. Do you have any thoughts on this? Oops. Would this be potentially compatible with how you're thinking about it right now?
Yeah, let's reset up the microphone. It's not stable at all. Okay, I'll just... you said not using numbers at all?
Yeah.
Interesting. So that would remove yet another language feature. Notice how compared to, say, Pirate or Racket, we already removed strings. I mean, you would still need strings for expressing text, but we don't use strings in the initial examples, so that's like one less language feature. I could imagine that one could go about replacing numbers as well, but at some point you see, well, at some point you want to transition to something that is more close to like the kind of Python that people tend to write, and removing numbers seems like something that people have, I mean, before we were discussing like how people have an intuition about the coordinate system because you're seeing it in high school. Numbers, you start like from primary school to see numbers, so even though they can be abused and they lead to all sorts of problems in terms of like hard-coded constants that need to be addressed, I don't think that, that I would take them away, but who knows, maybe that's an interesting experiment to try out.
Thank you.
While we fix the podium, maybe we can take another question. Yeah.
Anyway, can you say something about running it inside the browser? Like, how does that work, or what your experience with that was?
Oh, interesting. That's so there are experiments to run a Python interpreter entirely in the browser. There is a project, I think, in Rust to run an entire Python interpreter in the browser that mainly relies on WebAssembly. We would like to go there at some point, but we are relying on some graphics capabilities. In particularly, Pytamero is built on top of Skia, a graphics library made by Google. And that's, unfortunately, still not running in the browser. So what we are doing is we are basically executing it on the server, and then we are implementing some kind of caching mechanism so that we don't execute the same programs over and over again. But of course, we're just executing it in the backend. What we can do is that we can parse Python in the browser, that's already, and so we can figure out like some smart things, for example, showing just-in-time documentation links when students import certain names, or we can show like syntax errors, like the fact that there is a syntax error even before actually running the program. So that's what we're able to do, but who knows, maybe in one day we'll get there.
So just a super quick comment. We use Sculpt, which is a re-implementation of Python in JavaScript, and it also has the Python turtle.
Okay, yeah, that's interesting. So we will need to, support for libraries varies, and so we would really need to see what to do. Yeah, but that's definitely interesting future work.
Okay. All right, thanks everybody. So I think we're set up now. Okay, great. Thanks. Let's give the speaker a round of applause. All right, so the next talk will be by Kimio Kuramitsu on Kogi, a seamless integration of ChatGPT into Jupyter environments for programming education. Put this down gently.
Okay. Thank you. And good morning, everyone. My name is Kimio from Japan, and these co-authors are my teaching assistant working with me. Today, I would like to talk about programming education with ChatGPT in my classroom. Okay. So, digital era is coming at last in Japan. So, more and more students want to learn programming. Not only, thank you. That's okay. Not only CS majors, but also the high school students. And here, I want to just quick my introduction about my school. I'm working for the Japan Women's University. It was established in 1901, 100 years ago about. And my university opened up the computer science course about just 4 years ago. So I joined that school. But it's all students are women. But 4 years ago, when I joined my school, so only few students want to learn programming. But now, this is a picture about ICPC 2002 Japan regional competition. More than 30 students try to join such a competition. So that's so many students want to learn programming right now. And the programming environments are very important. It was first difficulty for students, but recently more easy to use tools to help people start coding, simpler for everyone to try. And this anime shows programming environments called Puppy. I presented in live workshop 2019, and more recently, I usually use Google Colab in my classroom. However, setting up the programming environment is not all difficulties for students. Students all students run into the errors. The error messages are very cryptic, and the solution isn't explained in the textbook. So many students stopped and frustrating about error when they occurred error, error. And more difficulty, error message in foreign language is more cryptic. So let's consider I translated in the error message into Japanese language. So they, in this situation, foreign language is more cryptic, and many students feel she is defeated. So today's keynote speaker said Python is hard because it's only available in English. And probably the best solution for students is asking a teaching assistant in the classroom, but the number of experienced teaching assistants are limited. And if students want to asking something, but they can't easily catch the assistants to teaching assistant. Teaching assistants are always around. So I want to change these situations. So my vision is using AI to respond to students' help requests timely. And it is important to note, I'm not going to replacing the instructor or teaching assistant with AI, but having something to help when they are not available. Our approach is using LLM, large language model. It's based on the deep learning techniques. And actually, 3 years ago, I started to developing LLM customized for programming educations for Japanese students like this. But about last year, November in 2002, OpenAI released the ChatGPT. The ChatGPT handles various programming tasks, and so I think let's combine the ChatGPT and programming environment. So I developed Corgi. It is an integrated Jupyter environment with ChatGPT. And the advantage for students is students won't have to switch back and forth between 2 screens. And let's show you the demonstration of Corgi on the Google Collaboratory. Okay, to install Corgi, use pip as usual. And this is a demonstration we already installed. And to start, you need OpenAI API key. But in the classroom, students can use without OpenAPI key settings. Just call the Corgi classroom login function. They register and secret classroom code. Students can start. And let's see how Corgi works. So here's a simple code, but errors happens. Once Corgi installed, the Corgi returned to the error about this. And also Corgi helps display the variables and to fix the code for students. But sometimes students can't help this. So they asked, what should I do? And the Corgi answered the connecting ChatGPT and answer the question. And they give the hint for fix for students. However, some students don't understand how to fix it. So they can ask the more direct request, to fix the code. At that time, the Corgi communicating ChatGPT. Okay, they give the fixed code for students. In addition, Corgi accepts any kind of request for programming. So here's a demonstration about the students guessing what is a panda. So she asks, what is a panda? So Corgi can answer that request in the context of their programming. Okay, this is a basic demonstration of Corgi. It's basically the chatbot between the students and the programming environment. Next, sometimes Corgi is very useful, so they want to use directly in laboratory, on the Collabo. So they ask the English or Japanese to Corgi interpret it prompt for ChatGPT, and they can pick copy and paste, and sample code is running. Also, students want to change, please change blue line to red. And Corgi detected the natural language from the code and sending the ChatGPT. Okay, you can get the advice from the ChatGPT, and you can copy and paste this code, and you can test to run. Okay, if you want to try Corgi, please contact me later. Okay, one of the most uniqueness of Corgi is it has a characterized AI. We set persona as an AI dog owned by teaching assistant in the lab, and learned teaching assistant conversation about programming. And Corgi respond a very friendly tone in Japanese. In English is not so friendly, but it's difficult for me to adjusting some tone in English. But Japanese is very friendly. And why I introduce the persona, prior to integrating ChatGPT, we have developed the LLM originally, and our LLM performance was very poor to call it as instructor or teaching assistant. So we needed something to represent encouragement of human humor. So that's why we introduced the characters of Corgi with my students. And my student likes Corgi, and they call the Corgi-kun with some respect. And here is the system architecture of Corgi. Okay, let's see the inside Corgi. So first, the Corgi is installed from the pip server, and once Corgi installed, it's add hook to the Jupyter kernel. And you want to run some code on the browser, so Jupyter kernel execute, and if errors happen, Jupyter kernel displays a chat, creates a chatbot. And using this chatbot, you can send help requests to Kogi. And once Kogi receives the help request, Kogi extracts the code and errors and names and variables, values of variables from the IPython kernels, and Kogi generates a prompt to ChatGPT. Here is a prompt generation. Our design policy, students are allowed to make a short message. Instead, Kogi generates prompt for accurate output. So students just say, what should I do? And Kogi regenerate the prompt, and they said, you are friend who running, they set a role such as you are a friend who running Python together. If you set a teacher, you are teacher, it's a little bit strong tone, and it's not for Kogi, and strong. And also, Kogi extract context from code, writing code and error message or variable names of something. And also, Kogi includes a student's request. And finally, Kogi sets a format and tone like this. And ChatGPT return to the answer, and Kogi is directly return to the Kogi helps. Current implementation, we do not filtering any response from ChatGPT, but in the future, we are planning to some filtering for ChatGPT's output. Okay, here is a summary of Kogi implementation. So, pros is almost everyone can use Kogi without confusion. Students do not need complex prompt engineering to use Kogi. And cons, result from prompt vary every time. Providing the same content in the same class is challenging. And also, the classroom is very affected by the update from Google or OpenAI. The behavior may unexpectedly change overnight. In the morning, I want to use Kogi, but sometimes Kogi not working. So the classroom is a little bit unscheduled. And here, we would like to share my classroom experience. Starting in April, it's a Japanese academics, starting a Japanese academic semester time, and over 150 students in our university trying Kogi out in the classroom. Mostly, we use Kogi, the two courses. One is introductory programming, and another is a data science course. And also, we should note here, all classroom was non-English speaking class, and every conversation and the question and the answers, the materials are used in Japanese. Here, the first question, did AI assist well in resolving errors? Here is a students' survey. Most students answer yes. And more to analyze more details, we collect weekly feedback, and we count every feedback, including the error problems. So this is 2 years ago's feedback, and this year's feedback, and this is a error feedback ratio from students. And apparently, the introducing Kogi is decrease the number of feedback from the students regarding errors. And here is a student, one of the typical student voice. And I always felt kind of bad asking the teacher over and over again. But thanks to Kogi, I could move forward my own more easily. And here is my observation. So Kogi is helping students as we intended. And students appear to maintain the high motivation to learn. Okay, let's see another analysis. So, which is easier to ask, AI or humans? So, here is a student surveys. And according to our surveys, the students tend to prefer asking AI. It seems a minimal resistance. On the contrary, we watch the usage in the first week. This is the number of requests for AI, and number of help requests, and number of students. And 30% of students did not utilize the Kogi even once in the first week. It's a little bit shocking because AI is very useful for students, but every student don't use AI systems. So, but students rarely ask the AIs even to AI. It's more often than the bulletin board. And also, I think I need to teaching students how to use AI with programming. So that's why the Kogi is evolving. And Kogi has updated several times during the semester. Our initial focus is helping help request for error messages. And we provide a limited function to students, but so this limited functionality reduces AI's accuracy, some kind of accuracy. So we need to improve the advice. So we decided to include the coding context as I explained. So it allows a fixed code. It's directly gets the answer, but I include a coding context and explanation of terminology and APIs more correctly. And recently, this is a demonstration version, directly prompting in the learn cell. So what kind of helps do students need? So as I developed the Kogi, I mainly focus on the error handling. But so improved Kogi can helping the many things. So they ask the terminology and they ask code. This means API is something, and they want to fix the code directly, and they sometimes say thank you for Kogi or something conversation. And this is a ratio. Easier to, and it is easier for teachers to track students' needs in the classroom. Okay, key insight from the classroom experience. On introducing AI, the concern about the potential risk of such as student cheating or something is, Okay. Overestimated. Motivation is important to avoid cheating. And the integration of AI and course materials presenting challenges. I think we can enhance the students' potential using AI, but many problems and assignments are too easy with AI. So what kind of assignments good for the students? So I would like to conclude my presentation. I would integrated Jupyter environment using ChatGPT for programming educations, and question about error is decreasing. But bigger question is remains. So it's not unclear the future of programming itself. So what should the educator prioritize in teaching in the AI era? Thank you for kind attention.
Okay, so we're going to have 4 minutes for group discussion about the talk. So if you're at a table with just a few people, maybe move to one of the bigger tables, and then we'll open it up for a couple of questions. Are discussions up? All right, so we've got a few minutes for questions here. Just raise your hand, and then please wait for the mic to get to you before asking your question, just so we pick up the questions.
Hello.
Yep.
So I have a question regarding the students' usage of this tool. Have you tested it with any students outside of Japan, and what responses did you get?
I'm sorry.
Have you tested the tool with any of the students outside of Japan?
No, it's only inside Japan, and so only my students, my university students, and my Japanese. I gave this presentation in Japan several times, and many professors want to use Kogi in Japan. So I want to provide Kogi for Japanese universities for the first time. But English version is almost ready, so I just...
Sorry.
It's okay. I think almost ready to use. If you want to try, please contact me.
The reason why I'm asking is because United States students are way more prone to cheating using AI. And I think Japanese students are, I guess, at least from the cultural stigma, more prone to following the rules that you said. So that's why I was interested to know if you actually tested with the US students, because they can get very creative with their cheating strategies.
Okay, I understand. So first time I just worry about the cheating, but cheating is a first problem, a top problem for me, and using AI properly is a first problem for me. And some students have, first time I lecture about the risk of overusing AI. So you damage your skill improvement or something. So that's why my students follows my instruction, but examination is exceptional. They use a lot. You don't use it at the examinations? This last semester, I allowed to use, all students use AI, and all students pass. But it's my problem. That's my problem. My problem. I believe too much.
Okay, maybe we can have the next speaker come up while the next question is being asked.
So, thank you for the talk. There was some discussion on this table about the learning happening when using AI, like ChatGPT in this case. We saw in the demo that there was a point where they asked, they had a problem like drawing the line, and they just asked ChatGPT to get the code. How do you see this learning? Is this part of like providing a worked example, or is it providing like direct solution without any like reflection from the student on this? And do you, for example, see it as a divergence from the focus on error in the first place and going then to the actual getting the solution or the working code without a lot of thinking about it? Thanks.
I'm sorry, too fast. It's difficult to catch everything.
So the main point is like, how do you see this affecting the learning of the students in the classroom? The learning of the concept, the programming concepts, but also, solving a specific problem by immediately going to ChatGPT and asking, give me the solution for this problem, rather than thinking about it and trying it out.
Okay, I understand. Thank you. Thank you for asking me. I think in the AI era, the concept and terminology is very important to ask the AI. And sometimes the students understand students don't understand the concept or something. But they can get the code. But I think it's it is really bad things, and students also know that it's bad things and meaningless. So I believe the students, she try to understand what code is like or something from AI. It's okay?
Okay, we've got to move on for the sake of time, so let's thank the speaker again.
There we go. Hello, everyone. Hello again for some of you that saw my talk earlier today. So I am going to talk about a framework for the localization of programming languages. So if kids start to learn programming, if they have a programming exercise, this is just something from a book, then very often in the first real programming chapter, the exercise is going to be adding two numbers. That's very, very often the first thing you see in programming books. And because my name is Feline Hermans and I work on programming education, this is something that I ran into. Some of you might have seen in the morning that I built a localized programming language called the XII programming language that looks like this. From the beginning, XII was a language that was bilingual in the sense that, as you can see here, the UI is in Dutch. All the buttons are in Dutch, the explanation is in Dutch. This is how I first made it. So it was always this system that was in two languages. But when we did our first user study, this was published at VLHSC in 2021, I asked kids, hey, how can we make XII better? And they wanted to have local keywords. That's the thing that they asked me for, which I was a bit surprised by, because I thought, well, Dutch teenagers, they will know English. Why do you need this? But it was a fun challenge to build, and you have to listen to your users. So quite early on in the process, we actually made XII be bilingual, so you can program in Dutch and English, and you may also mix the keywords. So vraag here is ask in my native language. And if you make a mistake, then, for example, you type vraag, then you get an error message, which is also localized. So very early in the process of building XII, the UI was localized and the keywords were also localized. So then I thought, very cool, my programming language is entirely localized. We are done. We have keywords in many other languages. But then Aladdin Sweden, my co-author, who's right there, he was like, yes, very nice, but what about Arabic numerals, right? Some of you have seen this before, but not everyone, that what I have thought for 37 years to be Arabic numerals, these things, aren't actually the numerals that actual Arabic uses. They have a slightly different character set. So these straightforward calculations that are very, very easy are only straightforward if your numbers, or my numbers, are the ones we are all knowing as Arabic numerals, which aren't Arabic numerals. So if you try Python, if you ask him to do 5 plus 7 in Arabic numerals, then you'll get an error message that isn't great. So then I thought, well, what else do I not know if I don't know about numbers? Maybe there are many other things that programming languages could localize in ways that I don't know about. So I thought, okay, this is going to be wild. So wild that it turned into a paper that me and Aladdin co-authored, a framework for the localization of programming languages, which describes 12 parts of programming languages that you could localize. So we're going to go over a few aspects of programming languages that could be localized, where you will consistently see that most of the design decisions we're making in tools for building programming languages like IDEs and parsing very much rely on English or Western thinking. So we have seen these two parts already of the framework, things that you can localize. You've seen non-English keywords. This is Dutch, for example. And you've seen non-English error messages. So these are things you have seen. We talked a little bit already about non-English numerals, but I want to dive a little bit deeper into the numerals. But first, let's talk about building programming languages. That's what we're here for, right? If you're building a programming language, probably you're doing more or less this, where you have some code, you have a grammar that describes what the code looks like, then you have a parser that parses with the grammar your code, and then if you have a parse tree, there's magical execution. It can be a compiler or an interpreter. Something is going to process this parse tree. So of course, if I ask you, what would you read or recommend if you want to learn how to build a programming language, you would say, the Dragon Book. Ding, 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 ding. Yes, the Dragon Book. Absolutely. If you look in the Dragon Book, like, what do they say about digits? Digits, digits, digits. What are digits? You can add them, you can subtract them. They are digits, but they are these digits, the Western digits. And nowhere in the Dragon Book at all, ever, do they really explain that these are English or Western digits. It's just like, these are digits. But the Dragon Book may be a little bit old-fashioned. What about learning a programming language in 2023? What would you recommend to younger people that's maybe more modern than the Dragon Book, that's more likely to be more inclusive? Third editions. I'm counting on my colleague who's right there. He knows what I'm going to say. Crafting interpreters. I love Crafting Interpreters. It is a fantastic book that's very, very readable. It's almost like a novel about someone building programming languages. I love this book. However, it too has this, right? It too has 0, my 0 to 9. So no one really seems to be integrating this. When I was an undergrad, I took like 5 compiler courses. None of these courses ever mentioned that there aren't only English numerals that are different ones. So this is why we live in the world we live in, where if you ask to do this in Arabic, you get error messages. And as I said also a little bit in my talk in the morning, this isn't necessarily very hard. You go to your grammar, and instead of having 0 to 9, you can just have the Arabic number for 0, interestingly enough, is pronounced as suffer, which says something about us building things. So you can go from suffer to tissa. You just add these characters to your grammar. It's not so very hard. If you actually try to type this in most editors, after you now hit the next key, this will happen, because it's trying to guess that you're in a right-to-left language, and it already starts to look very weird. But this just works, right? You just add this number to your grammar, and then you don't even have to change many things for it to just work. This is an example I showed earlier with a loop counter in a for loop. This just works, and if you want to, you can also have some conversion in the output. This is not so very hard. But there are other numeral systems. This is an example from our paper, just listing the most common ones that are used around the world, but actually the newest Unicode standard supports 58 different numeral systems. This is from the Unicode spec. So there are many numeral systems. Probably you don't want to manually copy them into your grammar if you want to make this change. But Unicode has this really nice idea of character classes, whereas this comes from our actual code base of Hedy. You can just do this, which just means all the number systems, even if we add new ones, they will be added to the character class, so this works. So it's not so hard, actually. If you are curious or interested in building this into your programming system, if you would just do this, then most of it will actually work on the parsing side. One more thing that's just very curious is I thought, being a Westerner, that if this is Arabic, you see that that is the digit for 10. The first thing that you encounter, going from the right, is the 1. And the next one that you encounter is the 0. So this would be 10. It is not 10. Actually, this is 10. It is the other way around. So the numbers are in our direction, even though all the text around it is in a different direction. So I didn't know this also, so we had a few errors because I didn't swap the number in the reading direction. So yes, many things I didn't know a few years ago about languages. So non-English numerals, we have covered them. And the interesting thing is I very much care about learning, right? I want to make programming languages more learnable, easier to learn. So I figured, If we are in a world in which we have Arabic everywhere, then of course if you have these Arabic numerals, this is easier to read. But something I learned also again from Aladdin is that it's also more usable, because if you are in a setting of Arabic on your keyboard, you'll have to switch keyboards if you want to mix Arabic and Western numerals. So here you have to do Arabic, you have to press a button to switch to English letters or numbers, and then you have to switch back all the time. And this is also, again, an argument in favor of having localization in programming languages, because if you are typing Arabic strings and English keywords, there too you would have to switch keyboards physically, going from this one to the other one with a button press or a mouse click. So it's not only about being more inclusive, it's also just very much a matter of practicality. So we talked about keywords, numerals, and error messages so far. Let's talk about right-to-left parsing. This is what I was most worried about, actually. I thought, oh, everything is the other way around. This is going to be very confusing because this is a heady program, but also this is a heady program. This is actually the easy part. It took us almost no effort to get this working because text in the computer is actually not stored left to right or right to left. It's just stored from the beginning to the end. And the presentation is up to programs. That has some downsides as well, but this, if you're debugging this, for example, here you have a little bit of Arabic code, the input string will just be the string as you see it there. So the first character is the first character in the reading order. For my Western brain, this gets really confusing, because if I now want to get the first character of this string, then I will get the first character, which is the first one there, these two. Firstly, this is confusing to me because I was expecting to get the exclamation mark, because I'm so used to having the first one being the left one for me. And also, this is the same letter. But it looks a little bit different. So depending on the next letter, Arabic letters can look differently, which is something you really have to get used to. And there's quite some software systems that do this presentation wrong because they do not connect the letters well, and then you get really, really weird results. There's one interesting aspect, though, in all the strings just being reversed. One intricate problem is this. What about brackets? So if you have this string in Arabic, the first bracket that you're going to read is a closing bracket. So now your grammar gets confused because it is opening, but it is actually closing. So here, one of the few cases in this whole adventure where actually operating systems were my friend, because this works, because actually fonts fix that. So if you're typing in a right-to-left language and you're typing a closing bracket, then it knows you want to do an opening bracket. It will store an opening bracket and show you a closing bracket. There's a little bit of magic right there. So right-to-left parsing just works. That was actually a thing I was worried about, but it was not so very hard to get done. So we talked about, right-to-left support is one of the aspects. If you're building a programming language in a localized way, at least you might want to think about what that means, specifically in terms of presentation and less in terms of programming language design. So let's talk about quotes. Quotes, you know, these guys. Or maybe if you're in Python, triple quotes or a backtick quote, or guillemets in French, or in Chinese. People use these type of quotes that are blocks because they can also be used like this. And interestingly enough, another thing I didn't know, Danish traditionally also uses guillemets, but the other way around. So like this. They call these goose eyes because it's like this. So this too is something that you could support, right? As I said also in the morning, it doesn't really cost you much to support these characters because probably your grammar isn't using them anywhere. Here again, this is not only a matter of being inclusive so that it looks like normal French, it's also very much a matter of ergonomics. Because in many European keyboard settings, you have a mechanism called a dead key mechanism. So if you want to type a letter in French or in Dutch that has an accent on it, you do that by first pressing a quote, and then pressing the letter. So if I'm teaching in the Netherlands, this is a consistent struggle I have, because I tell kids, you have to use a quote. And what happens, here you see it in French as well, I'm typing a quote, and this is what it looks like. This is what happens when you type a quote. In some settings, if you do this in Windows, it won't even show you the weird thing, it just will show you nothing. It won't show you anything. I see some nodding Europeans in the audience. And then you type the next letter, and then you get the accent on the letter. So kids are typing like this, and they're not looking at the screen because they're looking at their fingers because they can't type. So they type a quote, and then they type a letter, and then it does this. And they're like, but teacher, I put the quote there. And then it's not there. So in some keyboard settings, some quote symbols are just so much easier to access. On a French keyboard, guillemets would be easier to type, and it wouldn't have all these confusing side effects. So here you see that programming language design can take into account what operating systems are doing, but usually it doesn't. And then you get this very annoying behavior where a character that you pick for a language, you might say it doesn't matter, but thinking about where this is on your keyboard in different locales very much supports localization easiness. So we talked about local punctuation in one aspect, so we talked about quote, but there's so much more to talk about. Did you know, I didn't know this, that of course Arabic has commas, and think about our comma, it points towards the beginning of the sentence. So of course an Arabic comma also points towards the beginning of the sentence, so it's now pointing to me. And for reasons that are unknown to me and my Arabic speaking co-author, the comma also points upwards. We don't know why, but it points upwards and this direction. So this is a little bit of heady code that also actually works. So we also support Arabic commas and Chinese commas as list separators. So let's talk about culture. So different cultures might have different ways of interacting with language. This is very much true for the Arabic culture, where culturally it's not so common to depict humans and animals in art. That's not a thing that they do. So they have fantastic things like this. This is Alhambra Mosque in Granada, which if you look at it well and you know a little bit of Arabic, you will see that this is almost entirely letters. Like this is letters, this is letters. I got up to here, and of course, Aladdin was like, but there are more letters. These are also letters. All of these things are letters, right? And therefore, Arabic has all these very cool things they want to do with letters to allow them to make it prettier, which usually Western language don't do, like this principle that's called a tatwil or a kashida, which is a character that you can use to prolong this connection between two letters that we've seen before. Here's a little bit of Arabic writing, where you see the one in red is a very pronounced one, but also lower you see that the connection can be longer or shorter, so that the text is really lined out very well. So we have implemented already a few things, and now here's Aladdin saying, well, wouldn't it be cool if we could also support this tatwil, because if kids are learning to program, probably they want to prolong their connections. For example, here you have a little bit of code that just, it doesn't look nice. It doesn't look organized. Wouldn't it be nicer if you could do this? And you can, this runs, this is syntax highlights and runs, this actually works, so that you can line out everything. And this is, again, it's like two things. Like one thing is we're allowing people that come from different language systems to express their things. But also, I love this. I want to support print, so I can also line out my code like this, right? So it's not just about giving people access, it's also about learning from each other. Who doesn't like this? Like programmers, they like beauty, right? This is the thing we say, is clearly this is better than this. And you know what's not better? The grammar we need to support this. So again, if you're easily offended, you might want to close your eyes for the next slide. But you can also see on GitHub that this is our actual grammar. Here we go. This is my grammar. So in between all the letters, I allow an arbitrary number of what for you looks like underscores, but it's actually a different Unicode character. It's the tatwil. and it's supported everywhere. So I have a little preprocessor in my grammar where I split up all the keywords and put in between all these stat wheels everywhere. And because of the right to left layout, this last part with the 2 stars that looks like a smiley is very weird. That star actually belongs in the beginning, but it isn't also properly rendered. So you can imagine a world in which it would be very easy to do this, in which somewhere in your grammar framework you would simply say, ignore white space and ignore tattoo wheels, and it would ignore it in irrelevant places. You cannot ignore it everywhere, because if you use it in a string, you want to keep it there. So sometimes it has to stay, and sometimes it's irrelevant, like in a keyword. But we do not live in this world. We live in that world where this is my grammar, which I don't love, but it works, and you can create beautiful Arabic programs. So that's one thing, characters without meaning. We have a few other examples in the paper where some languages support all sorts of these characters, where it's not necessarily adding to the programming language in the traditional sense, but it's adding something. The things we've seen so far are easy. Right? This is all stuff, if you want to add this to your language, you can. It's just a little bit of changing your parser, and then it will work. And of course, the paper has some tips about how to do it. One thing that's a lot harder that we don't properly support yet is localized productions. So English has a certain order of words that not all languages also have. For example, if you have an if statement in a Python-like language, you will say if condition and then a tab and then a number of statements. And that sounds Englishy, right? So you can say if name is Jan, print hello, which is a bit like an English sentence. But if you're Dutch like me, this is not a sentence. This is weird. In my language, you would actually say, if name Jan is. This is the word order that I grew up with. And I have kids in my classroom type stuff like this, because it makes more sense to do this, if name Jan is, right? So then you will have to have a different production where the equality sign moves to the end of the line to create a sentence, which just, if you think about it, it looks really weird. Oh, sorry. It looks really weird if name Jan is, but this is our word order. And there's so many different word orders that different languages have. I see a Japanese person like, yeah, everything is different. Here's another example. In Turkish, you don't say while and then the condition. You actually say condition and then while. So iken is the Turkish word. So first you would say the condition, and then the keyword would come after. And then, of course, you're going to the realm of, yeah, that's going to be hard to parse. That's going to be hard to process, because first a condition and then the keyword. And there's so many examples of word orders that are slightly different. There's also this example in Chinese where the word in, like for I in range, is 3 characters, but then 2 characters go before the word in and 1 character goes after the word in. So you sort of split the keyword around the argument. This is all going to be very hard to parse. And also, the way we're supporting this now is people send me emails and I try to build what they want. But there's a very interesting user experience challenge also, is how do I explain to people what the freedoms are that we could support, even if we don't know if we're going to support it? People are not going to imagine, oh, but we could split a keyword. Oh, but everything could be different. So how to communicate about such a local production is also a very interesting challenge. So this is what we talked about. There's more in the framework. We have 12 aspects, actually, just to show you this is the things that we ended up not talking about in a brief talk. So variable names, diacritics, alternative keywords, and multilingual programming. If you look in the paper, we have a table in the paper which is sort of the meat, where we talk about all of these aspects in relation to actually existing programming languages. So here you see Hadi. Hadi supports the things we talked about, unsurprisingly, but Hadi doesn't support localized productions well. Fun fact, I had an SLE paper about this last year, but it hasn't made it into our actual code base because it's really hard. But then there are other languages that do support localized production. So I think with this we are showing both that these aspects that we're presenting are valuable because people support them, and also they're possible because people support them. So it shows that this isn't just a random set of hypothetical things that I think people could do. It's actually a set of things that people are already doing. But if you look at the entire framework, then all of them are supporting some of the aspects, but it's very, very hard to support all of them properly because all of them are really hard. And the more you want, the more generic your parser is going to be, the slower and the more cumbersome and the harder to maintain. So this has been a framework for the localization of programming languages. Do check out the full paper where we really go into detail about all these different localized programming languages and what to support. And try to, if you are building new programming languages, think of us. At least a few of these things are really quite easy to support, and it really makes a big difference.
Thank you. So we are entering into lunch territory here. Maybe we'll do an abbreviated discussion. We'll do a couple minutes, and then we'll have a question, and then and then we can maybe move the discussion into the lunch period. Okay? let's wrap up the discussions, and we have time for maybe a couple short questions or one longer question.
Hi. So you talked about a lot of the technical challenges of localization, and you started to touch on like the cultural aspects. But I think there's so many languages have like a formality distinction, right? Where in English, I don't care if my computer addresses me as "Yo, what's up?" But if the computer says the same thing to me in the Hindi or Marathi equivalent, which I also speak, I'd be a bit insulted. Like, you're a lowly computer. I am a human. You have to respect me. Say. The same.
I love that.
The same goes for like gender. Like, you know, in English you can just type in adjectives and the computer spits them back at you. But if the adjective depends on the gender of the speaker, then the computer can't just produce, like, you can't just say you are happy. It has to be you are happy, comma, masculine or something, right?
Yeah.
And again, this is also about inclusivity and making sure that all users feel like the computer is speaking to them and not assuming some masculine programmer. So have you looked into that sort of cultural or beyond the technical aspects of this localization stuff?
Yes, definitely. So most of the translations that we have are made by people that are native speakers. So they will take these things into account. For example, in, I think this is Portuguese, it says like hello with A and O at the end with a slash, so that you can be both male and female if you're the reader. These things also happen sometimes in error messages. The German translation has sometimes more the formal form than the informal form. So because of all of these languages are all contributed by volunteers that are coming from those languages and cultures, they are the ones that take that into account. In terms of language design, one thing that we didn't talk about is alternative keywords. So we do support, for example, is in Arabic can be male or female depending on the gender of the variable. So we don't just support one keyword, we support 2 keywords, and we can support multiple keywords for other languages. So a little bit of that is also programming language design, but a lot of that is like, I talked about this like it's my thing, but I started it, but we have these 47 different languages and we have hundreds of volunteers that have contributed to that, and then they're the ones that express it in a way that respects their culture. Sometimes they come ask me, like the Chinese translators or the French translators, like, what do you think we should do? And I'm like, you discuss this amongst yourselves, and I don't know, right? Because I want to empower you to do it in a way that you want. So it's also very much about letting go. It's really weird that there's this website with my name on it, and it has 44 languages, and I have no clue what it says. But that letting go, that if you do this with a group, then you trust them to take that into account. I don't have to like police all of that.
So, just wondering, who have used these language versions? Like, are there Arabic speaking students or other language speaking students? What's the actual teaching experience been like?
Yes, that's a great question. So maybe the best place to ask that would be on our Discord, where all of these teachers also hang out. Like, I can talk about my experience of teaching in Dutch, but Dutch and English, if you do like this, it is the same language. So it might not be the most interesting experience, but we have users worldwide. So our biggest users are, in addition to the Netherlands, Indonesia, Puerto Rico, Pakistan is really big, Hindi is also quite big. So there are people that are just more interesting for you to talk to. We have Japanese, we have Korean, we have different versions of Chinese. These languages are maybe more closer to the experience that you might have or you might be interested in. So I would say go on the Discord and ask people that are teaching right to left and non-Latin languages, because my half English Dutch, it's just not, I'm not the most interesting source of stories about that.
Okay, so let's thank the speaker again. Okay, and I think after lunch we'll have some introduction time, so try to get here on time after that, and I'm sure we'll have many more discussions over lunch. Thanks, everybody.
Okay, so I'm going to demo what these just-in-time intros might look like. So if we go to the next one, it should be me. Yeah, next one. Ah, yeah, that's me. Hi, I'm Molly. I'm an assistant professor in the US, and one of the things that interests me about SPLASH'23 are things like automatic feedback tools. I have a paper on that at SPLASH'23 a couple years ago. I teach functional programming, and so I'm always interested in making that better. And then also making sure that, PL concepts and the real world intersect a little bit better than maybe our students think. And that's it. So like a sentence about you, and then you pass it to the next person.
Okay, so hi, I'm Jesse Hopperks. I'm from the KU Leuven. I'm a PhD student. I'm working together with Feline as well. I'm interested mostly in teaching programming and increasing how we can teach programming by creating tools to teach programming. Also, automatic feedback tool is something I'm looking into. And I used to do pole vaulting. I really enjoyed it, but it has been some years. So if you want to know about that, I'm your guy, but I guess not. Next one. Oh, yeah.
Hi, I'm Afonso. I'm getting my master's in computer engineering here in Portugal, in Lisbon, and I'm also a teaching assistant at my university. Great news for you guys that like automatic feedback tools. I've come to present one. So I'm pretty much interested in anything nerdy regarding CS education, automatic feedback, evaluation, improving just the learning process of the students. And I'm just a cool guy around, I think.
Oh, that's me?
Oh.
Ouch. That's me. Hi, everyone. I'm a PhD student at the Università della Svizzera Italiana, that's southern Switzerland, in Lugano. Broad side of things that interest me, I've been involved in teacher training courses quite a lot over the last years for high schools. So teaching teachers how to teach, that's funny. And also teaching students how to learn, possibly, computer science, but other subjects as well. I'm interested in learning in general. And I guess I have to mention some kind of Swiss chocolate and Swiss mountains. But I still would say that Italian food has a sweet spot in my heart. Whoop. Oh, I think I need to get out of the set to ouch. I think it doesn't live update while, okay.
I'm Anjali. I'm a second-year PhD student studying PL. I'm interested in teaching. I haven't had a ton of experience yet, but I'm excited to teach intro programming someday. I'm interested in language design for learning and inclusivity in CS.
So this is me this morning. So I think you heard a lot about me. Things that interest me. I didn't write this. My grad student that's sitting here wrote that I like upsetting PL people. I think this is my goal. Maybe this is the result. Well, I care about teaching programming and inclusivity, and my hobby is long distance running.
Anybody else for a not slide related intro?
Yeah, you can just say maybe just a couple of words, even if you don't have a slide. That's fine as well.
Hi, everyone. I'm Tiana. I am an undergraduate student at Seton Hall University, and I am interested in developing tools to help students learn programming better in different courses. So, yeah.
I'm Marco Morazan from Seton Hall University. I work in programming languages and computer science education, and I try to bring to bear programming language technology into learning.
Yes, hi everyone. My name is Aladdin Sweden. I'm an assistant professor at the Open University of the Netherlands. And I am interested in computer science education in general, trying to help the students learn programming, especially with younger students and children, easier and better. Focusing on things like the work with Feline on the localization, but also programming misconceptions and their roots and how to improve the teaching material against programming misconceptions for younger learners in general. So that's it.
Awesome. Anyone else? Okay, so let's do a brief, small chat. We introduce ourselves globally, maybe at your tables, while we set up for our next talk.
How's your name pronounced so that I can
So
introduce
it's Tiana.
you? Tiana. Okay.
Yeah.
Minich.
Yes.
Okay. It's easy enough.
Oh, I was going to introduce myself, but it's
Oh, that's fine. Okay.
Okay.
Okay, so we're ready with the first presentation of this first session in the afternoon. This one is by Tiana, that's like my short-term memory, Tiana Minich. This is the first non-archival contributions that we have, and Tiana, the stage is yours.
All right. Hello, everyone. My name is Tiana Minich, and today I'm going to be showing you a visualization tool for non-deterministic to deterministic finite state machine transformation. This is joint work with Marco from Seton Hall University. All right, so formal languages and automata theory courses place a great deal of emphasis on constructive proofs. These proofs are very helpful because they help establish the equivalence of different computation models. Now, there's algorithms that help transform one computation model into another, but our focus today is going to be on NDFA to DFA transformation. So many students find this transformation difficult to understand. There is many things to keep track of, mainly because the DFA simulates all of the paths in the NDFA, which can mean a single path in the DFA can represent multiple paths in the NDFA, or a single state in the DFA, commonly referred to as a superstate, can represent a subset of states in the NDFA, or a DFA edge can represent multiple NDFA edges. Our tool solves this dilemma by visualizing a step-by-step addition of the DFA edges while simultaneously visualizing the corresponding NDFA edges by color-coding them. Now, we strive to have a low extraneous cognitive load, which means we want to keep this tool as simple as possible. So the only thing the student needs to worry about is navigating the arrows that help them step through the visualization tool, and then the appropriate message gets displayed that highlights the action being taken. Before I show you the tool, I need to give you a brief introduction to FSM, which is a domain-specific language embedded in Racket, and students use it to design and implement state machines. Now, today we're going to focus on NDFA, so this is an example of a machine implemented of FSM. So every NDFA has to have a list of states, the alphabet, which is just input that can be consumed, starting state, a list of final states, and the transition relation. Now, what we can do is we can call SM graph of this machine, and it will display an image of a transition diagram of the machine implemented. Now, as you can see here, is this pointing? Okay, cool. As you can see here, S, the starting state, is highlighted in green, and the final states, A, B, and F, are double circled. Now, final state A accepts all the words that start with A and are followed by an arbitrary number of A's. Final state B accepts all the words that start with A and are followed by an arbitrary number of B's, and final state A accepts empty word, which are all the words that can be accepted in this particular language. So the transformation that we use to implement our tool starts with creating a simple NDFA, and then we traverse a computation tree to search for the transition function, and then we use that transition function that we found to encode our DFA. Now, I'm going to show you this on an example. So this is an example of an NDFA that accepts all of the words in this language. So the language is just AB Kleenie star union, ABA Kleenie star, and then the Kleenie star of all of that. All right, so the first thing that we need to do is we need to find our first state, starting state, in the DFA, which is the superstate. So the starting state of the DFA is going to be all empties of the starting state of the NDFA S. Empties are just all of the states reachable from S by empty transitions. So in this case, it's just only going to be S. The next thing that we need to do is we need to find all of the states that are reachable on consumed input and all of the empties of these states that are reachable on an input. So from S, if we consume an A, we can go to either A or B, and empties of A and B, so just A and B. And on a B, as you can see here, we can't go anywhere. So when that happens, we note it like this, and on our DFA, this is going to represent a transition to the dead state. Now, we take our next superstate that we created here, and we need to see where it goes on an A. So from A and B, can't go anywhere on an A, so we're going to note that as a transition to the dead state. And on a B, it can go to C, D, and because we need empties of those, we also need to include S in our next created superstate. And we keep doing that until we get all of the superstates of our DFA. Now I'm going to show you the actual tool. So this is FSM, and here I designed the simple NDFA. This is the same one that I showed you in Brief Introduction to FSM, so it accepts all the words that are either empty word, or a word that starts with A and followed by an arbitrary number of A's, or a word that starts with A and is followed by an arbitrary number of B's. Now when this runs, as you can see, when we start the visualization, the NDFA transition diagram is fully displayed, and the DFA transition diagram only contains the starting superstate. Now, as you notice, this edge here is highlighted. This here is the starting superstate, Fs, which represents, as we said, starting state of the DFA, empties of S. So this edge actually corresponds to this superstate. And it's double circled because a final state in the DFA contains at least one final state of the NDFA, so that's how we know how to recognize them. Okay, we can step one step forward using the right arrow. So on an NDFA, as you might notice, this empty edge that used to be highlighted is now faded out because it has been used to construct something in our DFA, but it's not currently being used to construct the next edge being added to the DFA. On the other hand, these two, so we consumed our first input, A, as we did in the table, and we can go to either A or B. So these two edges are highlighted, and the corresponding edge is added to the DFA. So on an S, consuming an A, we can go to A or B. If we look at F, we're not going anywhere, so we're not adding anything to the superstate. And the message is displayed that shows us which edge has been added to the DFA. We can keep stepping. For example, this edge here you can see these two are faded out now, and nothing is highlighted here. Why? Because we tried to consume a B, but from S or F, B goes nowhere, so this goes to the dead state. Now we can keep clicking, and corresponding edges will be highlighted, superstates will be added. So here, for example, B on a B to B is also highlighted in the NDFA. But if we want to review one of our previous steps and look more closely at what has been changed in the visualization, we can also step backwards, which none of the previous visualizations have done, and we can do forwards, backwards, more closely see what exactly is changing, and the message is changing, the edge is being taken away if we step backwards, and the appropriate edge of this next to last edge added to the DFA will be highlighted. Now, what we also can do is we can press the down arrow and we can complete the visualization in one step. And we can do this from any step of the computation. So the last edge added to the DFA in a stepwise manner will be highlighted here as well because it was the last one added. It's a B on a B to B, and the corresponding NDFA edge is going to be highlighted. And everything else will be faded out in the NDFA because we completed the DFA. Everything has been used. We can step all the way to the beginning, we can play around with this, and that is basically the tool. Now, our future work includes adding visualizations for other transformations and constructors. We want to keep these visualizations consistent because once the student learns how to use one visualization tool, we want them to be able to use all of them with no difficulty. So the transformations that we've been visualizing are NDFA to regular expressions and regular expressions to NDFA, and the constructors are closure properties under union, clean star, concatenation, complement, and intersection. Now, if you want to learn more about programming in FSM or you want to adapt this approach to your classroom, this book is coming out later this fall. It's called Programming-Based Formal Languages and Automata Theory, and it is written by Marco. And that's it. Thank you for your attention. I will be taking questions.
So I would say we can still have a little bit of a moment for a roundtable discussion, given that we are kind of ahead of the schedule. And so we'll be discussing a little bit the talk, and then we're ready for the questions. Okay, so let's have like 3 minutes or so of a roundtable discussion. speaker? Plenty. Okay, that's great. Feature request. That's where's the issue tracker? That's.
All right, hi. So first of all, I just want to say that I think this is super cool. I'm a TA for Theory of Computation in my uni, so I really want to start using this in class. But one thing I did want to ask is, I don't know how standard this is, but in our classes, we don't convert directly from an NDFA with empty transitions to a DFA. We usually do NDFA with epsilon transitions, then a normal NDFA, and then to DFA. I don't know if that's like non-standard or something, because he seems to be a TA for Theory of Computation as well, and they don't do this. So I just want to ask if that's like, is that standard? If so, do you plan to support it in any way?
So that's this example that I showed is just an example of the language that does accept an empty word, but we just made it so if that's the case, if that's what the language requires, we can also do it with just like a final state that accepts the empty transition.
So if it just happens to not have any epsilon transitions, then it's just the same thing?
Yes.
Okay, it just won't have any empties. Okay, I guess that makes sense.
Yeah.
Okay, thank you.
So I was also wondering about, is it possible to, so we were wondering about the exploration of this. How can students engage with the system? Is it, for example, possible to execute the automaton and then see this is what it accepts in maybe an interactive way where it generates buttons for edges?
Yes, so this is just a little part of FSM. FSM is basically designed to teach formal languages and automata theory in like with the implementation, which hasn't been done before. So there's many tools that have been developed before my time that visualize the invariants, so students can actually prove that their machines work. Basically, the way they engage with it is they code up the NDFA. So depending on what they code up, the visualization is going to display different things. I had a question before, like, oh, but what if the students switch up the rules? Because as you can see here, this is my NDFA. This is my list of rules. Oh. So this is my list of rules, right? And if I switch up these rules, will the graph change? Yeah. And it will, because GraphViz generates these based on what we've coded up and based on the transformation algorithm. For example, I can run this one. I think this one's a little slightly more complicated, but if they design it differently, they're going to get a different tool and they're going to see different things. I guess if we have time at the end, I can show you other things in FSM, but it's all in the book that's coming out, and you can talk to Marco more about it because he's the one that made the whole language. All right, just needs.
Yes.
Right, yeah, like if
yes.
I pass it a string, can I see like the transition?
Oh, we can absolutely do that. We can absolutely do that. Okay, so for that you use SM-apply command, and then you do machine, right? Let me do the AAB. Let me comment this out so it doesn't run when I do it. AAB, and then you do the word, which has to be in a list. Let's see, what would this accept or reject? Let's do AAB. So this one is rejected because it starts with A, but is not followed by an arbitrary number of A's or arbitrary number of B's. But for example, if we put SM apply AAB of the word A, B, 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 this one would get accepted. So there's many things. There's also a thing that helps you see your tool, how it moves through the word. Let's see, AAB. You call this, and you can give it a word.
Nice.
You can give it a word. Oh, there's a graph view too, and there's a colorblind option too. And you can run it on this word, and the machine is built, and when you step through it, it shows you how the word moves.
That's cool.
And then at the end, it tells you whether your word is accepted or rejected. And this is not just for NDFAs and DFA, this is for all different state machines. We have we can also visualize Turing machines on this, or PDAs, or DFAs when not constructed like this. There's many features.
This is so cool.
Thank you.
Is this already available for us to use in our classrooms? Oh, that's so cool.
Yeah, it is.
Do we have time for one more question? Just out of curiosity, why Racket instead of like maybe some other language that's more what I don't want to say more standard because Racket's pretty well known, but I'm thinking like if I went to ask my first year students, do you know what Racket is? Like, oh, is it that thing you play? You know, they probably
yeah.
wouldn't know like the language. So I just wanted to know like if there was a concrete motivation behind using that language as opposed to something else.
No, our first years like to complain about Racket until they realize how awesome it is. I'll let Marco answer that question because he's the racketeer.
Okay. Do you maybe
So the short answer is that Racket is a programming language. It's easy to develop DSLs inside of Racket. So that's the path of least resistance is basically the answer. Right.
More questions? Okay, that's, I guess, one last round of applause for the speaker. And we're just ready for the next talk. Yep, I'll take care of it. Yeah, we'll wait. Just, we can set up maybe. If you want to set up. Just 3 more minutes to set up. So maybe we check if the connection works. Yeah. That's always scary. So that, yeah, if someone is coming in, they can still hear the talk. I'll set up the timer.
Is everything all right?
I'm okay.
Yeah, you okay?
It's not projecting.
Yeah. No, do you want it's because it's a break time, so the stream, it's not showing in the
Gotcha.
stream. Is everything all right?
Okay.
When start presenting, I'll show the slides.
Gotcha.
All right, I guess it's 2:30, so we can start with the first full paper presentation in this first afternoon session. This is by Marco Morazan, and this is about composing Turing machine in FSM.
Okay, hello everybody. So we introduced ourselves, so everybody knows who I am. So I'm here to talk to you about how to use Turing machines to build more complex Turing machines. Or like a friend of mine said, how to navigate the Turing tar pit. So, okay. Okay, so I'm going to try to do all of this in 15 minutes, so there's lots of time for discussion. Let's see if I'm successful. So when you teach a formal languages course, right, you talk about all kinds of state machines, and eventually that leads to Turing machines. But in this process, typically in a pencil and paper course, students get frustrated because they get marked down for buggy machines, they get marked down for proofs, based on buggy machines, and this goes against their computer science education because they're trained to what? To implement, to run programs, to write unit tests. In other words, to get immediate feedback on their designs. Right, so what can we do? So this is a programming languages course, and we're in what? The domain-specific language era. And so what we want to do is provide them with a DSL, which Tiana introduced as FSM. And so FSM does all kinds of things, right? So you can program NDFAs, DFAs, Turing machines, PDAs, multi-tape Turing machines, regular grammars, context-free grammars, context-sensitive grammars, regular expressions. The whole gamma is part of FSM. So I'm going to talk only about a small piece of that, which is the composition of Turing machines. So to build a Turing machine, we have a constructor, and every Turing machine has 5 things. So there is a set of states, an input alphabet, a set of transitioning rules, a starting state, a set of final states, and if the machine is designed to decide a language or semi-decide a language, the accepting state, which is optional because not all Turing machines decide a language. So here's a simple example of a Turing machine that moves the head to the right 1 space. So what we do is we specify the machine. So here we're saying that before the machine executes, we have the left-hand marker and the word on the tape, and the head position I is some position greater than 0. And in the post condition, the tape is not mutated, but the head has moved 1 position to the right, so it's k plus 1. So if we have 2 states here, S and F, and the input alphabet is AB, the starting state is S, and the final state is F. And you see that no matter what state you're in, if you read an A, a B, or a blank, you simply move to the right and go into the final state F. And that will move the machine 1 to the right. And then students, right, can write unit tests. So for example, we can show the transitions on our right machine on this input, and then they could see that it goes through those 2 transitions there, right? Turing machines can also mutate the tape. So here's an example of a mutator in terms of a Turing machine. So precondition, we have our word on the tape, the position on some position k greater than 0, and that position contains S on it. And in the post condition, the tape is mutated to the word is mutated to W prime. The head is unmoved, but now the value at position I is to a blank. And if we look at the transition rules, right, we have that no matter what state, no matter what is read, we simply write the blank to the tape and move to the halting or to the final state. And then again, students can write tests to make sure that, to validate, right, that their design works. By the way, feel free to interrupt me if you have any questions. Okay, so of course these easy Turing machines are not all that interesting. What we really want to do is build more complex Turing machines because in theory, Turing machines can do everything, right? So how do we do that? Right, so here's a slightly more complicated problem. Move the head 2 spaces to the right. So if we did this using just our Turing machine constructor, basically what we would have is 3 states, our starting state, an intermediate state, and a final state. And then from the starting state, no matter what is read, we move to the right, and we transition to the intermediate state. And then from that intermediate state, no matter what is read, we move to the right and move into the final state. Right? And basically what has happened here is that we repeated the code to move to the right twice. Now, if we're only moving to the right twice, that's fine. But if we want to move to the right 10 times, 20 times, or 50 times, that's not the type of coding that we want to do, right? So we need an abstraction. And so to avoid that type of repetition, we use Turing machine composition. Okay, so here's what we really would like to write, right? We want to have our tape, our initial tape, in the head at some position k, and then when we execute the machine, the tape is unmuted, but the head is moved 2 positions to the right. And what I would like to do is to take my right machine and use it twice. So here's how I would write it. Execute R, then execute R again, and halt. Now to write that type of things, of course, we need a syntax. So here's the syntax to write composed Turing machines. It could be empty, which means just halt. Don't do anything and halt. Or it can be the sequencing of a machine and then the rest of the machine. Or it can contain a label, and the label indicates where a certain machine starts, and this is what's used for looping. And then there could be unconditional jumps, which simply keyword go to and the label that you're jumping to. And there could be conditional branching, which provides the options of the symbol that's read and then the label that you want to jump to. In addition, we can abstract away the element that's being read by declaring a variable. And then the scope of that variable is the machine that's enclosed inside the parentheses here. And then if we have a variable declaration, then of course we can use that variable to mutate the tape and then continue. Okay, so basically there's 7 different types of expressions. And let me illustrate how you would design these. Right, so we saw how to move twice to the right. We just write R twice and we're done, right? How about something a little bit more complex? Move to the first blank to the right. Now what we want to do there is, right, we want to move to the right, and then we have to check what's being read. If it's not a blank, loop back and move to the right again and repeat the process. Okay, so here we have an arrow, and this is why we need labels, because these arrows indicate this is a point where you have to jump to. So here's how we would implement this. That arrow is label 0. And at label 0, we have the machine that moves right, and then we have a branch. And if it's A or B, we branch back to 0. And if it's a blank, we go to 10, and 10 is the machine after that is empty, so the machine will halt. Okay, so and then you can see in the tests that this machine works as it's supposed to. So if, let's look at the one test here. Right, we're in position 2 here, so that's the first A, and then we move to the first blank to the right, and that would take us to this blank here, which is in position 6. Okay. Okay. Now, how about this example where we're writing the 2 elements to the right to be the same as the element that's currently being read? So in this case, we want to declare a variable S that abstracts over what's being read. We move to the right, we write that variable, that value, we move to the right and write that variable again. And the implementation looks exactly like the picture. Right? Here we declare our variable. So whatever is being read, that's the value of S. We move right, and then we can use S to mutate the tape. And then if you could look at the examples, right? So here, for example, we're in position 1, that's over the A. And we want to write 2 A's after that. So what happens is we write that A, and we end up in, the head ends up in position 3 of the tape. Okay, so this brings us to a more complex example. This is not the example in the paper, so hopefully with what's in the paper and this, you have 2 examples that you can kind of work with and play around with. But what we want to do is add 2 natural numbers. Any idea how? How do we add 2 natural numbers? Yeah, you look like my students in class. I have no idea how to add 2 natural numbers, right? So it's at this point where I have to remind my students to remember everything that they've been taught and everything that they've been learned, right? So for somebody who's followed a design-based program, the natural thing to do is to think about the structure of the data that you want to process. And this means defining it. So a natural number, in our case, will be either a list containing only a blank in it that represents 0, or it can be a list that contains a D and then followed by a natural number. And here are some examples, right? So that represents 0, that represents 3, and this represents, if I can count right, that represents 8. Correct? Everybody got that? So pretty straightforward. Okay. So now we specify our machine, So we start with the blank before the A, the head on the blank before the A, then we have A, then we have a blank before B. That's where we start, and what we want at the end is to have the starting blank, the sum, and then the head on the blank after the sum. Okay. So how do we do that? Whoops, yeah. So what we want to do is reason about that structure. And this is, right, animated problem solving or how to design programs, bread and butter. So what we're going to do is we're going to move the head to the right. Remember, it's on the blank before the A. And then there's two options there. Either A is 0 or it's not 0. So if A is 0, we'll branch this way. If A is not 0, we'll branch this other way. Now, if A is 0, what do we want to do? Well, we want to figure out if B is 0. Right? So now we say, okay, move to the right twice, and now check what B is. So if B is not 0, then we have to figure out a machine to process A equal to 0 and B not equal to 0. And if B is 0, then we look at this situation where A is 0 and B is 0. And then what do we do when A is not 0? Well, we have to skip all of A to get to B to figure out if it's 0 or not. So we go to the first blank to the right, we move to the right, and then the same thing. We determine if B is 0, or we determine that B is not 0. And what we've done there, right, is this is your bread and butter divide and conquer, right? We've divided into, hopefully, 4 smaller problems. But usually when you use this type of structural recursion, the subproblems are always easier. So we're in safe ground here. Okay, so let's look at the 4 cases independently now. So if both of them are not 0, what do we do? Well, we're going to start with the D, with the first element of A, which is that first D. We're going to move to the blank that's between them. We're going to mutate that D, the blank, to a D. So now we have A plus B plus 1 on the tape. Then we're going to move to the blank at the end, after B, move to the left, and then mutate that last D into a blank. And now you have, you see, the post condition. We have A plus B between the 2 blanks at the beginning. Okay, and then we're going to do something similar for the next case. A is 0 and B is not 0. And it turns out that for that case, the same steps apply. So by this type of analysis, we discover that these 2 cases, when A is 0, we apply the same rules. So we can implement that like this. Move to the first blank to the right, write a D, move to the first blank to the right, move left, blank out whatever is there, and then halt. Okay, so we have part of our solution already. Right, this branch here that used to break into 2 branches is now solved using that code. Now we're going to do the 2 other branches. So what if both of them are 0? Well, if both of them are 0, right, remember we've already moved to the first blank to the right and to the right, so we start there in that configuration. And since the sum is 0, all we have to do is move the head to the left and halt. And if it's the last case where, yeah, that's how we implement it. If it's the last case, let's go to the last case, here we go, where B is not 0, then we're on the first D of the B, we move to the right. And now you see we have the answer on the tape, right? A, 0 plus B is just B, but it's in the wrong position. So we shift it to the left once, and that puts our head at the end. We move to the first blank to the left, shift again, and now we have the post condition, right? The sum is there. So that part is implemented this way. Left, first blank to the left, shift left, halt. Right? And now we have all the pieces that we need to actually code up our machine. Right? So this is what it looks like, right? So there's 4 arrows, so you need 4 labels, plus the label where the machine halts. Right, so 100 is the label when A is 0, 200 is when the A is not 0, 300 is the machine the part of the machine that's going to process when A is 0 and B is not 0, and 500 is when A is 0 and B is 0. And then 1,000 is just when you want it to halt. Okay? Now, how do we know that this is correct? By the way, just so that everybody's a believer. Where is it? Okay, let me run this. So here's an example, right? So in this case, they're both not 0, and when I run that, you see that the tape ends up with the sum of A and B on it. Okay. Okay. So now, how do we know that this is correct? Right, well, key word in this course is formal, right? Formal reasoning. So we want to use formal methods. So we're going to teach, we have students do correctness. And for that, we just use Hoare logic. Right, so we start with the configuration of the tape. And at the beginning, the head is on the blank before the A. Okay, so once that's done, what's the first thing that it does? It moves to the right. So what's the configuration after that? Well, if it moves to the right, there's two options, right? We already know this from our design. Either A is 0 or it's not 0. If A is 0, the head is over a blank. If it's not 0, the head is over the first D of A. Okay, so then what? Now we branch, right? And that's going to tell us which of these two situations we're facing. And so if we branch to 100, then we know that A is 0, we're reading a blank. And if it's not a blank, then we're reading the first D of A. And we're in this configuration. And now we keep adding the Hoare triples and just drag these assertions through the machines that are part of the program. So we move to the right. So the right, that's easy. One to the right. We move to the right again. So it's either here, reading a blank because B is 0, or it's on the first D of B. And then we branch. And that would be to the 500 or to the 300 for both of those cases. Now, more interesting, what happens when A is not 0? We move to the first blank to the left. So we're on the first D of A. First blank to the right, I'm sorry, is there, right? So now we're after A, the head is after A, and we write the D there, right? So that's easy. So now that blank is mutated to a D, and then we move to the first blank to the right. And again, right, that's the first element of B. It could either be 0, it could be blank if it's 0, or it could be a D. And then again, we move to the left. And what we want to do is whatever's on the left, we're going to turn it into I'm sorry, where I got lost now. First blank, move left, yeah. And then we turn that into a blank. And once you turn that into a blank, if you look at that, right, that's our post condition, right? We have the sum in the right place. So we can safely branch to halt, which is label 1000. And we're going to do the same thing for the branches as 300. I won't bore you with the details, right? Everybody gets the gist. And the same thing, right? But the important point to point out to students is that no matter which path is executed in the Turing machine, the post condition is always met before jumping to the halting label. Okay? Okay. So Tiana kind of jumped the gun on me, so if you like this approach and you would like to adopt it, there it is, right? It's coming out. It'll be in December. It'll be in print. So I encourage you to take a look at it, adopt it. Send me lots of questions, because the biggest complaint I always got was, I want to do this, but we need a textbook. So I heard your complaints. There's the textbook. FSM is available for free on GitHub. So just search my last name in GitHub and you'll see FSM. Okay. And for the discussion, if you guys want to try your hand at designing a little, right? There are a few problems you can try out, or if not, or if you have questions, feel free, but I'll let you guys discuss now.
All right, usual time for group discussion. That's very different than most formal languages courses, right?
That's what I was saying at the beginning, that it's pencil and paper, which is more difficult.
Right.
Now they do everything inside a programming language, everything. And there is no pencil and paper.
For context, which
This is juniors and seniors, so upper level students.
okay, so they already have like at least a couple of years.
They're not beginners. Yeah, they're people who are graduating that year or graduating the next year.
Okay.
Towards the end.
So they already know how to program. Right. Oh, okay. All right, I guess we can bring the discussions to the speaker. Questions, if you raise your hand, the mic will magically get to you.
I had a brief technical question. So there were the pre and post comments. Are those parsed and like used as part of FSM, or are they just comments? Cool.
Picking up off of that comments question, do you think it would be feasible or viable to actually use those comments for something? So that all that reasoning that you did, do you think there could be a way to like parse those comments and then automatically reason about the machine? Or maybe I'm being too ambitious here.
No, I don't think you're being too ambitious. It's just I don't want to parse the comments. What I want to do is I want to re-implement this using Calc or something like this, and then have an automatic theorem prover.
All right.
Prove,
that's that kind of stuff.
Prove
Yeah.
that the machines work correctly.
Oh,
So that's the ultimate goal. This is just
that is
work
super
in
interesting.
progress.
Thank you.
We have to write these down and prove. No, fine.
Yeah, but if you could have like an automatic proof, like this machine works, here's the proof,
Yeah,
it's automatic, that'd be super cool.
Yeah.
It's already super interesting. I'm not like criticizing.
Don't be shy.
So this may just be the fact that I'm a compiler developer, but when I was looking at this, I was like, wow, it would be actually kind of fun to write the thing that takes, I assume that you provide the sort of compiler from your little DSL to the actual thing.
Yes.
But I also think that there is a certain category of nerd, and I may be sort of one of the only people in that who are like, oh, well, but what if I could do that part myself? Like, that's an interesting advanced exercise, maybe.
Yeah. So one of the biggest motivations was, that motivated development of FSM was that students were not getting non-determinism. They just completely didn't get it. So I decided that what we need is a programming language where this is a feature, and not have them worry about how to implement non-determinism. So it's a compromise. Okay.
We can thank the speaker then.
Thank you.
Oh, okay. Oh, sorry guys. It's my personal laptop. There's a ton of stuff on here. All right. Okay. I can wait. It's fine.
Right, and I guess just in time we can start our third presentation for this session. This is WITTER, a library for white box testing of introductory programming algorithms. Ooh, you all are coming in. That's good. And Alfonso, the stage is yours.
Thank you so much. Before I begin the presentation proper, I would just like to point out that my co-author Andrea is right there in the audience. So if there's any questions that I feel like he might be better suited to answer than I am, I'll definitely tell him to come up here and take the pressure off my back. So I'd just like to tell you a little bit about the things that we'll be whittering on about today. If any of you are familiar with the expression, that's going to be very funny. Otherwise, please ignore it. So I want to discuss a little bit about one of the problems that we've identified with automated assignment assessment in introductory programming courses. We're going to talk a little bit about that, and then we're going to talk about the approach that we've developed to tackle that problem. We're going to talk a little bit about what it is, how it works, what we've implemented so far. I want to show you all these cool things that already work, some examples of how it works, and then at the end we're going to leave a little bit for what we've planned to implement in the future, and then a little bit of time for discussion and suggestions, which we very much appreciated. So the main goal of our work is to identify and tackle one of the problems with automated assessment of assignments at introductory programming levels. So what is this problem that we think we've identified? Is that usually when at an introductory programming class you're evaluating students' assignments, you do it in a black box manner, which I assume everyone's familiar, but for those, if anyone isn't, that means that the assignment only takes into consideration the outputs of the code. And while that works for a lot of implementations, we feel as if for students that might not be descriptive enough to gauge what the errors in their code were in a straightforward way. They really don't take into consideration many aspects that could be relevant. For example, I reckon most of you have probably either taken or are currently teaching, I don't know, like an introductory algorithms and data structures class. That might be relevant to like see the algorithmic complexity of what the student has implemented, like how many loops I've executed, how many array operations were executed. And usual assessment solutions really don't take that information into consideration. And while you can technically and usually augment some, for example, I'm sure most of you are familiar with JUnit for Java. While you can generally augment those kinds of solutions, by, for example, if you want to measure the running time of a student's program, that's usually quite easy. You just use a timer or a clock that the language provides. But if you want to go more in depth, it usually gets very complicated very quickly. There's things that you can gauge using like static analysis, maybe if you do metaprogramming or reflection. Some of you might be familiar with that term. And if you want to go really in depth, you can do code instrumentation, but that is just very, very specialized, and it's a headache to implement. So it's really not accessible to most practitioners or instructors. So obviously that raises problems and frustrations. For example, I'm sure most of us have either gone through that or have students going through that right now. This raises a ton of frustrations. So if I have a student implement an assignment and I tell them, oh, your function's wrong because I was expecting it to output 100 and output 50, okay, that's all fine. That's true, but like, I don't know why it output 50. Like, why did it output 50? I don't know. Like, I thought it was right. I don't know why this is the way that it is. Or like, okay, I knew it was going to output not the correct result. Like, I don't know what I'm doing. I'm really not familiar with programming. I've never done this before. But I actually needed the tool to tell me what was wrong and how I could have improved. And if it just tells you, oh, the result was wrong, that's why you got it wrong, that's not very helpful if you don't know what you're doing, really, if you're at a base introductory level. And of course, this raises frustrations like, oh my God, I really wanted to help me. I really wanted to know what was wrong. I wanted the tool to be able to guide me a bit more. And we found that usually leads to frustration from the student side, which is obviously something that we want to avoid. And then obviously from a lecturer standpoint that I feel like some of you might relate to, when you want to grade the assignments of maybe a class that has like 500 students enrolled, you can't do that manually. It's not feasible. So you have to come up with an automated solution. But I think one of the main concerns that you might have is, okay, how am I going to write tests that cover, I mean, in theory, potentially 500 different solutions, right? You cannot possibly account for every single minute detail that students could change. Or I don't know, like tell them to implement a specific algorithm and they implement another algorithm that does the same thing. If you only check the results, then obviously it's going to produce the same thing, but you want to check that they implemented the algorithm that you want them to implement. So how do you check that if the only thing that you're taking into consideration is the result of executing the code? And then finally, as I've talked about augmenting these solutions, you can be worried that maybe, okay, if I want to augment my solution, do I really have to go and take time off of grading to learn all these extremely difficult solutions? Obviously, that makes it not very accessible to most instructors. Like, you have things to do. You can't go and stop teaching to go and learn a new specific avant-garde library that allows you to test these things. So how do we think we can tackle at least some of this problem? So we've developed Witter, as I've said, which is a library for white box testing of introductory algorithms. And from what I've described so far, obviously it's developed with students and lecturers in mind. And our main goal is to make the process easier on both sides. So from the instructor, we want them to be able to easily specify test cases for student assignments, including those in-depth ones that I mentioned, without having to have specific knowledge of what actually goes on inside. And then from the student, obviously we all know students don't really want to have that much work, so you don't want them to have to do anything differently. They just submit their code. The code that they've already implemented, the usual thing that they do, they don't need to do anything differently. They just submit the code, and that's what's evaluated. Essentially, what Witter does is it takes the instructor's solution, which we'll analyze in just a little bit, and it takes the student's solution. It executes and compares the two, does its magic that we'll analyze in just a bit, and then at the end we get a list of feedback results that lists some things such as the tests that were passed, what metrics we were evaluating on the student's code. If they were wrong, then what was the result that I was expecting, and what was the result that was actually produced by the student's code. And these, of course, seem very standard for any evaluation solution, so I'd like to give you a little example of how this could actually be used in a classroom environment. So say that you're an instructor and you want them to implement some algorithm that you want to assess. Basically, what you have to do is what you already do. You develop your own solution, right? You want to have a reference solution that you or yourself develop. So you develop that, then what you do, or what we want you to do, is annotate your solution with some extra information about what should be tested. So you implement your solution, and all you have to do is add some annotations in comment format that specify what should be tested. We'll go a little bit more in depth about this in a second, but I can just give you a quick rundown. So what this piece of code is specifying is that for that procedure that we called sort, just descriptive example, it's going to run it for 3 different inputs, so with these 3 arrays separately. Then for each of those, it wants to keep track of how many array read and write operations were computed during the execution of the method, and we also want to check for any side effects that were produced on the argument that was passed. Obviously this structure, as you can see, if you're familiar with it, follows the usual Java annotation syntax. This is both a practical and a design choice. In the design standpoint, we know that Java is a very common language, so most instructors will probably be familiar with this syntax. And then at the university that we teach at, they learn Java in their first year, so it will be probably very accessible to them as well. As for the student, they don't really need to do anything differently. They implement the algorithm, and then that's what gets graded. They don't need to do anything differently. So with this in mind, what we can actually measure so far is what I've just told you. Instructors provide their annotated reference solutions. Student provides their regular solutions. And as for things that we can measure, so far we've implemented the measuring of things like return values, which you can use for obviously regular black box testing. And then if you want to go more in depth, you can measure some white box results such as the side effects on an argument, how many loop iterations were run, how many array and objects were allocated, how many times was an array read or written to, and how many recursive calls were executed. So to make this a bit more clear, I'd like to give you some examples. So a very standard, simple example. Let's say you have the student implementing a recursive factorial function, right? So this is probably what most of you would do if you were programming in Java, just a standard implementation. You might do n = 1 here instead of 0, but that's not important. So what we're saying is that the student needs to implement this code, and what we want to test is to pass the integer 5 to this function. We want to check its result first and foremost, and then additionally we want to check that the students, we want to keep track of the students' recursive calls, and then what this one here means is that the number of recursive calls in the student's code needs to be within a margin of 1 of ours. Again, because you can do n = 1 or n = 0, they're both equally valid base cases of recursion, so we don't want to restrict them to doing exactly like we do, so we add a little margin of error. Say maybe the students, first year student, maybe not very familiar with recursion yet, so they try to sneak by implementing an iterative solution. So, basic factorial iterative solution with the added artificial defect that we started the loop here at 0. I don't know, maybe a student's very used to doing loops starting at 0, it's very common, but they forget that they're multiplying things here, so their result is always going to be 0. And then once we pass those 2 solutions to Witter, this is the feedback that gets outputted. And I want to point out that these are not artificially constructed examples. Well, they are in the sense that we had to come up with them, but this feedback was not written just for the conference. We actually implemented the tool up to a point where we could test these, and this was actually the produced output. So what can we tell from this? Obviously, their function is not implemented in general, like it doesn't compute the factorial. Why? Because for the factorial of 5, we were expecting 120, but we got 0, so there's a mistake there. But then where we can check that their algorithm itself behaved unexpectedly was that they didn't implement it recursively. Why? Because we were expecting 4 recursive calls within a margin of 1, but they didn't execute any recursive calls. So immediately we can tell that they implemented an iterative solution. So that gives us much more information that we could gather from just a purely output-based evaluation. Another standard example that you would find in many introductory algorithms classes, the binary searching algorithm, which I'm sure all of you are familiar with. Let's say the instructor provides this solution. Very standard. I'm not going to go into details of the code. Let's just note that what we want to be tested here is we want to find the number 1 in this array, and then another test case, we want to find this number in this array. And to check that the algorithm does what we want it to do, we want to keep track of the number of loop iterations that were computed. Again, maybe the student is very familiar with the binary searching algorithm, so they try to sneak on by using the linear searching algorithm. Much more easier to develop, but it's not what we want them to implement. So this is the code that they provide us, just a regular linear search implementation. We run those 2 solutions through Witter, we get this. So obviously, in here, the black box tests are going to pass, because they're both searching algorithms, so if we want to search for a certain value, they're both going to either find it or not find it, because they're both searching algorithms. So from only that, we wouldn't be able to tell that they didn't implement the correct algorithm. But if you look at the more in-depth metrics, so namely the loop iterations, we can check that the algorithm certainly doesn't match what we implemented. We don't know which one it is, but we just know that it doesn't match the one that we wanted them to implement, because we were expecting like 4 loop iterations and we got 8, or we're expecting 3 and we got 1. You got the idea. Final example. I don't want to bore you too much with tons of code on screen. The insertion sorting algorithm, another one that we have special contact with in our class. I'm a teaching assistant for an algorithms class, so this is, I see this every day. I ask students to implement insertion sort, and I provide them with a solution that looks like this. And let's say that I want to test it for simplicity. I'm just going to test to see if it sorts this array here. And to guarantee that their algorithm is correct, I want to test the number of array read and write operations. And I want to check what side effects the procedure produces on the argument that was passed. So I'm expecting it to be sorted. So I'm expecting 1, 2, 3, 4, 5. So the student doesn't really like insertion sort. I'm assuming that they're very, very nasty here, so they implement selection sort. So this is a standard implementation. And when we run those 2 solutions through Witter, what we see is that obviously the black box test is going to pass. The side effect on the argument is going to be the same because they both sort it. They're both sorting algorithms. They just don't do it in the way that I want to. And I know that because when I look at the number of array read and write operations, it doesn't at all match the algorithm that I wanted them to implement. So again, what I want you to take away from these is that from the purely black box test, we would not be able to take any conclusions about the algorithm that the student implemented, only that it produces the correct result. But if we look at these 2, then we can tell that the algorithm, surely something must differ here, right? So how is this all implemented? I wanted to pique your interest by showing you examples first, but now I want to talk a little bit about how the magic happens under the hood. So Witter runs on another library, a library called Strudel, which was developed by my co-author André, that basically provides an interpreter that allows us to listen for detailed code execution events. So it executes the code as an interpreter. It basically simulates the JVM. And it lets us listen, for example, to loop iteration events on it, or method call events. Lets us listen to several code execution events. And what we do is, I'm going to show you in a diagram in a little bit, but what we do is we capture that listening system. We gather information as the code executes, and then from that we construct our so-called evaluation metrics. Which brings me to something that I want to mention. It's not in the slides, but I'll talk about it in a little bit. For the annotating of our code, we developed our own little grammar using Antler. We call it the test specification language. Sounds fancy, doesn't it? It's just a simple grammar that we use to specify those annotations. I'm not going to go back. To specify the annotations so that we can actually save the information that we want to test. And then we use the Java parser library to parse the arguments on the annotations that pass the arguments to the test case. We use the Java parser library to parse that information that we can then pass to Strudel that actually interprets that code. So essentially, the workflow for the code being executed and the listening of events that I just mentioned is you take some piece of Java source code, you pass it to Strudel, that loads it, interprets it, constructs an AST, an abstract syntax tree, and then interprets it. So it runs the code. And then obviously it runs it, so it has access to the outputs of the code, and that's what we use to do black box evaluation of the algorithms. And then where we really do our magic is that we hook into the listening system of Strudel, and we can access those code execution events to construct the white box evaluation that I mentioned. Obviously, this is all very cool. I might be biased, but I think it is very cool. But there's still a lot of stuff to be implemented. For instance, we want to implement the capturing of additional runtime metrics. Obviously, recursive calls are cool, return values are cool, array reads and writes. For example, in the example that I showed you about reads and writes, it might be easier to reason about something like array swap operations. At least in introductory algorithms context, it's very common for one of the cost models that we use for algorithmic complexity to be the number of array swap operations. So that might be easier to reason. Obviously, the more metrics that we can capture, the more information that we can give the students, which is also one of our goals, which I'm going to get to in a little bit. I feel like I'm going to get to a lot of things in a little bit. Aside from array writes, we could also check for variable roles, for example. Say in that factorial example that I showed you, I think it would be interesting to be able to measure that the variable that ends up as the return value, that we could check that it actually acts as an accumulator of the result, for example. And of course, we would appreciate any feedback and ideas, which I'm hoping will come along in the discussion phase. Another thing that we want to implement that we assume is probably going to be the most difficult one is stateful testing, which basically means that we want to run sequences of instructions and have the state of the test persist between the two. This, of course, broadens the scope from just static procedures to data structures, which would also be extremely useful in a data structures class, which is also introductory. We do think that this will pose quite a challenge because not only will we have to find a way to annotate data structures with comments that let us specify solutions that should execute sequences of instructions and persist the state between them, but we'll also have to change the way that we provide the feedback to the students, because obviously if you're running 5 or 6 methods on the same data structure, it doesn't suffice to just say, oh, expected this and got this as I showed you in the previous examples. So we think this is probably the biggest feature that we want to implement next, but we also think would be the most challenging one. Again, I mentioned that this was developed with students in mind, so obviously we want to encourage them to be autonomous and creative. So if we restrict them to a single correct solution, that goes against the exact opposite of that goal. So we want to be able to specify the inclusion of multiple reference solutions, and we don't really think this will be challenging. Just add some annotation that specifies an alternative, then run the student's code against all of them and choose whichever gets the best result. It really doesn't matter there. But this, of course, goes along with the fact that we develop this with student creativity and autonomy in mind. We want them to learn. So if we're restricting them to a single solution, that's super restrictive. That doesn't go along with our goals at all. And then on that note, of course, we have to run tons and tons and tons and tons and tons and tons of tests. We want to really assess how Witter affects the learning progress of students at this level. So we want to see if the inclusion of white box feedback actually lets us access information that could have gone unnoticed in typical black box software testing solutions. If that information does get passed, we want to see if the students can actually use that information to reach correct solutions faster or in a better way, if it is beneficial for their learning. And of course, we're going to have to do some work on how we structure the feedback because we want it to be readable and understandable. So if you just give them a mess of, I know Feline talked in her presentation about the EOF expected, like, we're going to have to do some work on the feedback so that we want it to be understandable for students that might have not have ever coded before, and they still have to take this class. So we want to do tons and tons and tons of tests. The part of testing and how it affects the learning process is probably going to be the focus of my master's dissertation. So I don't know, maybe we'll see each other again, I hope. Yeah, that's really all I had for you today. Thank you so much.
All right, you know the drill, group discussion. All right. Lively discussion. Time. Oh, that works. Lively discussion. Time for questions. Raise your hand as usual.
I feel like you got the sneak peek, though, from the co-author.
Oh, sorry. Oh, thank you. No, actually, I was just explaining to him what we are doing, and what we are doing is using an interface, given that you use Java. So we would, instead of working on an array, we would have a sequence list, whatever interface, and have then the students take this as an argument and work on it. And then, of course, when I'm testing, I plug in my own class, which can then completely track whatever's happening. Is there, so I like what you approach, because that I would love for my programming class, where I really want to force students to use certain programming constructs. Where in the algorithm class, I'm more interested in the order of process. Do you see a particular benefit on the technical side that you check in the algorithms class, for instance, whether they're well, how they're accessing the array in an order, or would you see it equivalent to use an abstract interface?
Okay, so it's actually interesting that you mentioned that example about modifying arrays, because that's one of the things that actually motivated the development of Witter, was that I wanted to assess if students actually implemented the correct sorting algorithm. So what I was doing was I was introducing my own class that kept track of the intermediate states of the array, but what I was finding is that, they can loop from left to right, or they can loop from right to left, or they can loop, starting from the middle and doing, so there was a lot of cases that we could, that you'd had to take into account. And also what I was doing with my class, or what I tried, was that if I didn't run the code and checked what happened, I would have to do static analysis, which was a headache. So what we ended up concluding was that it would be easiest to just supply a multitude of reference solutions, maybe even just implement some construct that you could add into the body of the method, says, oh, this can be also in the other order. And then all you have to do is execute the code and just does the comparison automatically for you. You wouldn't have to actually specify the tests that takes into account, oh, the array must have been this and this and this and this and this. You do your solution, and then it just compares automatically as the code executes. So I guess it saves some work. Thank you for the question, by the way.
Yeah, so thanks for the talk. So you're using your solution as the ground truth, but, well, people make mistakes when writing solutions, and when I do this as a teacher, I almost always make mistakes in my reference solution in the first try.
Right.
So then I use my own test to fix my own implementation. But if you're using your solution as a ground truth, I would assume you sometimes run into trouble with being wrong.
Okay. Well, I would argue that you can you can input your solution as the ground truth into our tool once you verify that it actually works. You can test your own solution, and then once that's all nice and verified, you can then add it into our tool, and then that's used as the truth to verify student assignments, because you're assured that your solution already works.
Okay, but so I can't really.
But I get your point. I'm not trying to discredit you.
No, I get it. But so I have to use another tool to test my solution and then plug it in. So I can't do it within your tool.
In order to be certain that it would not, that you wouldn't have any errors on your part, I guess you would have to test your solution beforehand. Yes.
So isn't that a reason to just let me write the expected result in the test within the annotation? So I have the test as well there.
I guess it would be. We did try that initially, but well, do you want to help me out here?
Yeah, I think it's a good point. We discussed that. It's something easy to do, and it's like a pragmatic reason. So
yeah,
I agree with the suggestion.
Our initial implementation actually just had the annotations where you specify the arguments and then comma and then the expected value. So initially, the first alpha version, you would implement to that, but then we switched over to it comparing to your reference solution. Because I think what we ended up arguing was that, okay, the professor's already going to have his own solution, so they don't need to do anything. Just slap some comments on there and use that as a reference,
No, it's a good defense, I think.
Yeah. Thank you.
Thank you. So I have a laundry list of questions for you. Tell me when
Oh, no, okay.
Tell me when to stop.
Oh, God, I'm scared now.
So some of the metrics that you're using, you're counting this and counting this and that. But I could see this completely different implementations producing the same matrix. So I'm going to take your factorial example. If I wrote that in tail recursive form, I would get exactly the same metrics that the same measurements that you're getting, but it's not written in the way that you're prescribing, which is using structural recursion.
I guess you're right.
Right? And then related to that, think about something like quicksort, for example, right? If I get to pick, if I don't pick, I get to pick the pivot, right? Which one I want. Depending on how I pick the pivot, you're going to get different results.
Yes.
But it is the algorithm that you want.
But one of the things that we thought about in that regard was why we added the margin of error. If I just go back a little bit, maybe to show you. When I described that for the factorial implementation, we added a margin of error for the factorial's recursive calls.
To what?
I guess in any sense, we can just specify whatever number we want. So if we want like, oh, if it's within 20 iterations, then it's technically right. That might be a bit exaggerating, but you could, you don't have to restrict to a specific.
Yeah, so I'm going to give you something to think about, right?
Oh, God, okay.
Think that the vector is already sorted.
Okay.
Now, if you always pick the first element as the pivot, it's a completely different performance as if you pick something else that will more evenly balance the two subtrees, the two subsets that have to be sorted.
You're right.
Okay. So just food for thought.
Thank you so much. Yeah.
Yeah. And the other question I have is, what about exceptions? Are you thinking about how right, programs have exceptions?
We have not yet, because obviously this is like a proof of concept. I'm going to implement more things and then analyze how it affects students. That's going to be the basis of my dissertation. There's just sort of a prototype to demonstrate the practical feasibility of implementing this as a library that could be integrated into other systems. But of course, if we want a full-fledged release implementation, then we would have to think about things like exception handling, or if the exception is meant to be thrown, then we would have to catch that and accept it as a correct solution. Obviously, in a release scenario, we would have to, but for this prototype, we have not handled those yet. Thank you, though.
Yeah, food for thought.
Oh, of course, yeah.
All right, I guess, well, one very last quick question, and then we wrap up, so we don't eat into the break time as we did for the lunchtime.
Yeah, just a quick question. Thanks for the presentation. I asked it in the table as well. It's about the scale of the feedback that you get with this tool, and in relation to the size of your program or algorithm. So maybe you will have another algorithm, a bigger one, or multiple algorithms, depending on your assignment, of course. And then you will get also a lot of different metrics that you as a teacher, bringing you back to the motivation, you could also have a hard time knowing what's happening there.
Okay.
So what's your thought on that?
I think when we were developing this, we were taking into consideration what we could see at the university that we work at, and what usually happens in intro to programming or algorithms and data structures is that assignments are very, very isolated. So one assignment could be, okay, implement quicksort, or one assignment could be implement insertion sort, or one assignment could be implement binary search. So we usually give them very small, isolated, specific assignments. So that's where we focused our attention for now, because of course we're going to want to run tests later, so it pays to have something that can already work with what's usually happening at our university. But of course, if you have like an implementation that needs 20 functions to be implemented, obviously you're going to get like a feedback that's going to be hard to read. Yes, that would be a problem for bigger implementations, but that's not what we were focusing on for now. It would need to be addressed if we wanted to support bigger implementations, of course. Thank you.
All right, let's thank the speakers once more. And it's now coffee break time. See you in half an hour for the last session.
Excited to welcome you to the last session of Splash E today. We have two great final paper presentations, and then I'll put up some discussion prompts, and we'll end the day by kind of summarizing, right? What have we learned? Where are we going towards that past, present, and future theme that we have for this year's Splash? But to begin the session, I'm excited to introduce Rose, who is live streaming from Massachusetts, to talk about centering humans in the programming languages classroom, building a text for the next generation.
Thank you for the introduction. So let's get into what this talk is about. By the way, can you please mute the room? I'm hearing myself and it's distracting me. Okay, so the outline. So there are 5 parts to this. There is the introduction of what the project is, what's about. There's a description of the text that's copied. I'm then going to do a description of what I have done to the teaching now and sharing stories from my students in the classroom. This is a research paper, so there's also some data analysis that I did to inform the text. And the people to look at that. Okay, so this is talking about the development of my new open access textbook in the programming language and critics with it. This is focused more on the process behind developing that project. For anyone who wants to read the book or the course materials, the links and the QR codes are at the bottom of the slide. So the audience of this book is it's aimed at fit into basically the PL elective slot in a CS curriculum, so it's upper level. At the same time, I'm proud to say it's the first truly interdisciplinary book of this kind with shared emphasis on programming language theory and human computing. So the role that it has, rather than being aimed primarily at people in an HCI program, is to give that breadth and to basically open up some of these human-centered design discussions to people whose day-to-day core is more on the program side. And so the scale that we're looking at, it's a 20-chapter textbook. It's about 100,000 words of text. The last time I converted it to a PDF, it converted to about 600 pages. All right, and so the way that I like to motivate this, for the sake of rhetoric, is we can ask who takes a programming languages course, because each book and each design have a different underlying idea here. Some people say courses are taken by students who want to know a lot of different languages. This is that old idea of the PL zoo that's been heavily criticized by PL educators. A second kind that I've taken plenty of in my own graduate studies is courses that are designed for students who want to do a research career in programming language foundations, programming language theory. Okay, we've got great textbooks for this. And the third one, this is perhaps the style that I taught before I started building this book, is that students are also taken by people who want to become programmers for a job, and they want to have a strong understanding of their tools. And it's not that we don't need any of these courses. There's a reason these courses were developed. But the underlying idea of this new book and this new course is a radical different way of answering this question. The idea being that programming language courses are taken by students who will need to work in interdisciplinary teams in the future, who need to work across disciplinary boundaries, and who need to be able to understand programming languages as a breadth, stacked up both by data and by place. We are from school, but it's also backed up by the fact that the last time that I taught the graduate PL course last year, only 25% of my audience were graduate students in computer science. We have people in robotics, in data science, in computational media, games, also a lot of undergraduates. And so we really need to be able to keep this technical core in there while tending to a very diverse audience in terms of technical interests. And so the way that I scope this just to look at the 2 courses I teach, or 2 of the 3 courses I teach, I should say. So in my undergraduate course, we're usually looking at CS majors with about 3 years of prior experience who have worked in interdisciplinary projects before. Most of them are comfortable with multiple programming languages and not comfortable with proofs. In my graduate course, we've got all different kinds of majors. We've actually got plenty of undergrads and all the way up to PhD as well in that same classroom. Very wide range of experience, but very few of them are comfortable with proofs, except for perhaps PhD students in my lab. To give you a sense of what's in the book, here's the outline of chapters. I included length estimates from the platform. So we start out with kind of the CS core. And what I'm doing is I'm giving them review of things they may have learned in their formal languages course, moving on to core ideas like inference rules, operational semantics, defining type systems, abstract syntax trees. But I'm doing all of this with implementation work they can do to tie into their existing skill set. We then have the next core area being sort of an HCI core, drawing both on ideas from the social sciences and even some ideas from critical studies in the humanities. So we do everything from how to design a user study with quantitative and qualitative methods to bringing critical perspectives from gender studies and disability studies. Because I have substantial collaboration with our games and media program, there's kind of a whole sub-module on case studies in media. But these aren't just case studies in the sense of a zoo. These are case studies that are used to reinforce everything they learned in the 2 core modules. Because I am also still active in programming language foundations and theory, we also have things that are meant as kind of a teaser or an advertisement to students who might be interested in advanced research level study in those areas. Okay, and interdisciplinary work is always hard, and designing an interdisciplinary curriculum is no different. So I settled on a core pedagogical strategy for designing the textbook. The core here is that there are these 5 core characters called the archetypes, which stand in for different academic disciplines and perspectives on the design of programming languages. The core goal I emphasize in the course is not to be an expert in every area, but to have the ability to communicate and to be literate across these different disciplines, and to use design as a conversation that can bring all of these different archetypes together. Those archetypes disproportionately represent computer science. This is an intentional decision. So we call the practitioner our person who's programming for a job. The implementer is someone who implements programming language technology, such as writing an interpreter or a compiler. The theorist is someone who sees a programming language as a formal language and sees a good programming language as one that supports powerful analyses or powerful static guarantees. The social scientist is someone who studies humans, often empirically through an experiential lens, either for the sake of humans or for the sake of design when working in an HCI context. The humanist is also looking at humans, but they're often focusing more on structural critique, stemming from critical theory, rather than an experiential approach that might be informed by qualitative research. So in designing the book, when I design the exercises, I make sure that there are things that each archetype could sit down and want to do. It could be as simple as writing a function in the language of your choice. It could be implementing core language technologies. It could be to have some theory without having people do a lot of proofs. I have things like doing derivations of context-free grammars, determining the language of the regex. This is a compromise in terms of the level of theoretical difficulty. For social scientists, we can have things like autoethnographic studies, all the way to corpus studies about discourse that programmers have. For humanists, I have prompts for essays that you could slot into classes in cultural studies, gender studies, disability studies. These also exercises aim at multiple complexity levels. These range from things that I would slot into an exam, reasoning through an example, the example semantics of a program, type checking examples, regular expression examples, to things that would be appropriate for an undergraduate homework or project, things like implementing a specific feature or running a user study. And they have some prompts in there that are research level that are really meant as something for people that are either doing a PhD or master's thesis. So speaking of the assignments, the way that I make this work, and it has worked very well, I just finished the first undergrad version of this class, is that I split things into a coding assignment spoke and a written assignment spoke. The coding assignments are auto-graded. The written assignments are participation graded, relying on intrinsic motivation and kind of peer community to ensure high quality. So start off giving them some toy programs in our language of choice. I have chosen to run this course in Rust, but the book is designed to support multiple languages. They then write a parser using parsing expression grammars. They then write an evaluator as part of an interpreter. They then write a static type checker. And at the very end, they've switched into design mode rather than coding mode, and they do some coding to support their data analysis. On the written side, they start with goal setting. They brainstorm a study before they've seen the techniques they need. They reflect with some autoethnography. And then later on, they've seen the techniques for design, and they give a detailed study plan. We spend a day in class running the studies, and they write up their results from that study on their final written project. This is built to scale. This is something reviewers ask me about, and I did it this way because I need to scale. Time, 85 students, most one TA, one out of research load. And so this is something that is designed for people. The language choice of best is something that's important for class because class can ignore language choice even if book can. I base this on my learning goals, students' unstated opinions, and what I know my students are. What is being to implement their evaluator and type checker, their parser, into steps. So my work is for them to have statically typed language with object data types and recursion. Based on something they're oriented, I need to motivate it to them that way. Even though it's not something that has wide yet, it's a growth thing, and they respond very well to that argument. In addition, they have prior exposure to systems programming, a little bit of exposure to functional programming, but zero exposure to that type of This is because what this allows to do is look on their knowledge of C, and then this is a starting point where they explore all sorts of deeper, more advanced languages in Rust, and this worked well. So I want to share a few stories from my students. The first one, a letter a student sent me at the end of the beta version of the graduate course in spring. This was fully project-based of the course. And so coming in, he talked about how he didn't have any interest in theory until he took the course, but going through this process made him more interested in the theory than he was before. He really enjoyed freedom of design, and it was something where this structure made him feel motivated during an otherwise tough term. In the full letter, he talks about how there was, he worked maybe more hours than he should have, but actually felt satisfying because the motivation was tied in with it. So the second story was from the version I just finished, and I wanted to show how the user study work can serve as an opportunity for creative exploration among students who might in CS might. So we had one student who wanted to learn whether posture affected a programmer's productivity. He hypothesis, and half the class is on the front program, and half of them slouch at their table in program. And so it was hard not to laugh. It was hard not to get tape. But as the teacher, I felt this was very good at the class because this gave an opportunity for a nerdy technical group of people to start seeing each other's interest and taking them to laugh together without compromising urban. Okay, the third story was that after the user study, the final homework had an opportunity for students to do some creative coding in any of the media creative-oriented languages that we use as case studies. Out of 57 homework submissions, 19 students chose to do that. We had things like fractals, cartoons, and text adventures, but one really stood out. So without me prompting this, one of the students, wrote time text adventure game using Rust for their implementation, and I could not think of a better way to reverse the desired takeaway message of this project, which is that the PL the designers and all friends. So I'm going to run through the analysis, see proper amount of conversation. What I did is I analyzed 3 courses and my feedback from 3 courses in a course evaluations to guide the design of this project. The old one was an IPL course based on Sriram Krishnamurti's textbook PLAI. The graduate version take project-based beta test using like handbook. And another one was an info program course. So I have feedback from the latest version that uses the full book, but it wasn't in time to submit the paper itself. So I looked at people's sentiment toward ungrading, things that we learned was that they felt it increased their intrinsic motivation. That's the biggest one, the impact on learning outcomes. The second was instruction. There were some students that expressed concerns with rigor when I was doing a fully project-based course. That was what brought us to use this combination of largely auto-graded with aspects that are more unrated, facilitated. Language choice was something I talked about in the context of a course. I personally love bracket list programming. It was something that was unpopular in that introductory context, and that led us to explore alternative choices. I also, in feedback, social issues in the classroom. I will say during that graduate course, we were talking about social issues in class. As a transgender professor, there's actually kind of a natural experiment that happens very rarely. I saw more of this when I was in early transition compared to before transition. We should be aware that women professors get more than male professors do. The good news is that as I continue to hone this, I've gotten pretty good responses from this latest version of the course. All right, so future plans. I now consider the course to be released. I am still revising it, adding content, and looking for an open access academic publisher. This is something that really could not have happened without community, and it is something where I hate that I couldn't be there in person. I really want to look for opportunities to chat and collaborate with people. So if you are interested in using any part of this in your classroom, I would love to talk and support you with that. I also want to add things in future editions of the book. I want to emphasize the research styles and research that gets done by including interviews from interesting people in the research community just to whet students' appetites. And if you would love to be interviewed, I'm happy to do that. I also want to include some art. One of my dreams is to draw some comics of the 5 archetypes to kind of motivate students in each chapter. If you're interested in being involved in comics in any way, that would be perfect. One of the chapters we most want to add, you may have seen similar things from Felina's keynote earlier today and Felina's research paper as well, is we really want to build out discussion of supporting programmers with different native languages. And so it turns out one of the, and also just cultural aspects of PL design. It turns out one of the best case studies out there is based on classical Chinese, or in Mandarin you call that Guwen or Wenyuan. My Mandarin's fine, but my Guwen is not. And so if we have anyone proficient in that, I would love to talk to you about some of that work. And that's the end of my slides. I'm about to turn it over for questions. But this really was something that was developed in community, even though it's a solo author work. And so I want to acknowledge all the people who helped make this happen, whether it was people that encouraged me, gave feedback on the paper, people who gave me advice on their lived experience with disability and programming languages, or even people who just encouraged me to pursue this kind of broader research agenda. Thank you, and that's the end of the talk.
Can we, great, there were many claps. I'm not sure you were able to hear that. Just to give you a little bit of context, I think most of us followed most of that. There were some internet issues, but not worth interrupting the speaker. So you may get some questions just to clarify parts of what might have been missed. Just to remind everybody how SPLASH'23 is working, we're going to take 4 minutes to have small group discussions in the room about the presentation, and then we'll share out Q&A afterwards. So if you could mute the in-room mic. Mic on? Hello. We've had some great interrupting conversations to keep going with the session. Are there any questions in the room for Rose?
So you described the 2 tracks of the course, and we were wondering how that fits in a single semester.
So that fits in less than a single semester because I teach that in a 7-8 week term at WPI. So I can tell you how it fits. And really, the way that makes this work is I find that when students have some priorities in place, that really helps them. And so the way that the course is structured is in the first half, it's very heavy on teaching kind of the technical coding kind of stuff. And then, your homework is due after the lecture finishes, right? So there's some time in between there. And so there's a bit of catch up where they have some time in the second half to reinforce that kind of stuff, finishing their assignments. And then the written homeworks that go with it, those are graded based on whether you hand in a complete attempt that you make an expert on. And so what's going to happen is the students that are weaker or more, stressed for time, they're going to kind of do the minimum there, and they're going to pick up some of the information, but not as deeply. The students who have time to put in the extra effort, who are really motivated, who are really into it, they're the ones that finish the coding faster, and they're the ones that go above and beyond and put in the extra effort on the written. And we did have some people that did that. We had people that did things like put together a little game for a project. So it's about priorities, basically.
Hi. So I'm interested to know why you picked to use Rust for this course.
Good. So the motivations were in part based on community. If I wanted to do something that other PL education researchers have shown interest in, RAC is absolutely one of those, but Rust is another area that has been receiving that kind of attention. Some of it was based on a mix of personal interest of my own, since I've done some work in linear type kind of situations. It's something that I've wanted to do more of, but also something that I could motivate to students. So it's something where I can point them at the stats for language popularity and show them, oh, it hit the big popularity index for the first time this year. Oh, it's showing year after year growth. It's also at the same time something where I can give them some of those challenges, some of those features, but at the same time I can point to them. And what I'll do in a lecture is I'll say, here's a type error in Rust. Here is the thing you did in your C-based course, where C has a bug here, and Rust turns it into a type error. So it's something that I have a foothold to teach them a more advanced language on.
Hi, Rose. Feline here. Thank you for the book. I really love it.
Hey.
Here's a question. There's something that I've been struggling with teaching a similar course without your book, is that students already have a conception of what programming language research is, or they will learn about it in undergrad, and I think it's like semantics, basically, and POPL stuff. So when I started to teach, but also interviews are PL research, but also observation studies, I literally had a student say in class, yes, teacher, but there has never been a POPL paper like this. So are you sure this is PL research? Which I think is an understandable question. So I think that my question to you is there's really a big difference between the world your book describes, which is a world I would love to live in, and the world we live in now, where PL research is only 3 chapters of the book, and I don't know how to deal with it. And it started sometimes to feel like I was giving sort of a sermon to my students, like, yes, this is all very true, but they didn't really believe me. They thought maybe interviewing people was my hobby, and therefore it was valid, and they didn't believe me. I don't know how to deal with that.
So I will say, if you come up with a perfect solution to that, I will buy it from you. So I think there is partially an institutional aspect here. I'm almost, not quite, but almost the only PL person here. And so if they have no one else teaching them PL courses, well, whatever I say is PL, that's PL. But there is still that aspect of concern about respect and legitimacy, which is something that, I did grapple with in earlier versions. Some of the tricks that I've used to do that are, one, to make sure there are thorough scholarly research citations throughout the whole book. So when I ran my beta test of talking about things like gender and disability, they felt like it was just my opinion. But with the new version, the proper version of the book, I can go through and I can show them, here's High paper, here's a VLHCC paper, here is a paper in a gender studies journal, these kind of things. And that shut up people a little bit who need to be shut up. And the other aspect that I've done where I give myself the right to shut people up a little bit is on the first day of the class, I lay out, here's what this course is. This is half a CS course, this is half an HCI course. If you are not comfortable with the human-centered part of this course, I expect you to drop. It's okay if you don't know, if you don't have background, but if you're not open to learning about people, that is your choice, not mine. So that's what I've done so far, and that seemed to work.
Great. Thank you so much for the presentation. Let's thank our speaker again. I'm not sure you'll be able to hear the claps, but they are happening. And if, Rory, if you wouldn't mind, start sharing so I can introduce your talk.
Okay.
Rose, that was awesome to hear about.
Thank you.
Let me just go live. Is everything working?
Yes, we see your slides and your face. Lovely. So the last presentation of SPLASH-E this year is going to be exploring engagement and self-efficacy in an introductory computer science course presented by Rory Kelly.
Yeah, all right, awesome. Yeah, so I'm going to be talking about exploring engagement and self-efficacy in an introductory computer science course. I'm Rory, and Megan is also here in the Discord chat for questions later if they come up. And we're both from the University of British Columbia. Quickly, just to introduce what the project was about, giving a quick overview. We wanted to conduct an exploratory study on the relationship between engagement and self-efficacy in an introductory computer science course. So the course that we're using is for non-CS majors, and many of those students do not continue on in CS, but for those that do, this would be the first course in the software engineering stream that teaches foundational software design principles. Throughout the study, we used the experience sampling method that I'll describe in more detail later, which involved regular interviews targeting engagement and self-efficacy fluctuations throughout the term. We were looking for correlation between interview responses, student disengagement, and losses in self-efficacy. And just really quick to touch on, I am a very recent graduate from the University of British Columbia, and Megan is the actual professor of the course that the study was held in. However, we kept the data from Megan until the course had concluded in order to meet ethical concerns in that regard. So we might be wondering how we chose to define engagement and self-efficacy for this study. So engagement encompasses various dimensions, including behaviors such as effort, persistence, and concentration, reactions such as interest, happiness, and anxiety, and psychological aspects such as a student's own investment towards learning. Self-efficacy, on the other hand, refers to students' belief in their ability to succeed in a specific domain. It influences the student's motivation, persistence, and performance. Essentially, what it breaks down to is engagement is that day-to-day granular interaction with the course and how that affects the students mentally and emotionally. And self-efficacy is that overarching belief in their ability to succeed and enjoyment of computer science as a concept. The experience sampling method, for those of you who do not know, involves measuring feelings, thoughts, actions, and/or activities by collecting data in context of a participant's life, utilizing repeated measures to track a participant's experience, often using electronic devices or interviews to prompt responders to give their responses. And these data collection intervals can either be time-based or event-based, and an event in a course such as this might be every time a student finishes a homework or after a tutorial or things like that. So as this was an exploratory study, we wanted to find research gaps that we could address and try to find certain solutions for. So we realized there was very much limited research investigating the development of self-efficacy and engagement in computer science education, both of which are concepts that have been shown to be very important for a student's success in other disciplines. This gap is even larger in relation to the experiences of non-CS majoring students that are taking an introductory computer science course. And additionally, the experience sampling method, we believe, could be used a lot more in the context of computer science education in order to investigate students' experiences. So ultimately, we came to the purpose of our study that we were going to try to identify, which was how do international non-CS majoring students' engagement and self-efficacy fluctuate in an introductory computer science course. We also had a secondary goal of finding what caused those students to disengage from their learning. But as we'll see later, this kind of became secondary due to a slight lack of qualitative data that was able to be collected. To give some more context on the study specifics, we used a course at the University of British Columbia that had 42 international students and was meant to be a first-year course that is introductory and assumes no prior programming knowledge. It was intended for students who do not plan to major in computer science and based on the How to Design Programs curriculum, focusing on a systematic approach to program design. The participants were about a third of the body of the class. They're all international non-computer science majoring students and were those students who consented to join the study from the entire class size. For the data collection, as I mentioned earlier, we use the experience sampling method. For our purposes specifically, we use an event-based sampling that was done after each of the tutorials in the course. This involved 2 to 5 minute interviews of in-person data collection conducted by myself. Each week, I would ask consistent questions so that we could then kind of compare the responses as time went on and see how the responses from the students fluctuated throughout the course. And these questions were really designed to focus in on the students' engagement and self-efficacy as the course went on. Here's the interview schedule. So the course was a shortened 8-week summer term course. So there's only 8 weeks of instruction, and it followed the designing programs curriculum. So we started with Python and functions and moved into some different data types, list data types, and more advanced functions analysis programs, visualization, and the projects that the students would conduct. And for those middle 6 weeks is when I conducted interviews. So the interviews were largely kind of retrospective for what had happened so far in the course, as well as honed in more specifically on how the student felt since the last interview as well. So a lot of the times the interviews would have a lot of content, mostly from the week of instruction that had just happened. So it kind of syncs up with the topic being discussed. For the interview questions, we used inspiration from previous studies on effective self-efficacy questions for measuring that aspect of a student's experience, as well as a study on how to design an engagement questionnaire. And we opted to go with 3 self-efficacy questions and 5 engagement questions. The self-efficacy questions were statements whether the student agreed with the following. I feel capable of doing well in the course. I feel interested in the course materials, and I feel proud of my accomplishments thus far. The engagement questions were, have you been enjoying class? Has the course been moving at a reasonable pace? Have the course topics been interesting to you? Has the course been too challenging? And if so, what has been the most difficult part? And do you feel that you have learned new skills? For the data analysis, obviously, it's a lot of qualitative data, so we're able to dive into what students found to be the most difficult and what they did and did not enjoy. But we also wanted to have some quantitative analysis, so we decided to kind of classify student responses on a binary scale or 3 scale of 0 for no responses and 1 for yes responses, with a 0.5 for kind of things that obviously lay in the middle. And since students were from an international background, maybe didn't have English as a first language, we found that the responses were often shorter and simpler, so they lent themselves very easily to this either yes, no, or somewhere maybe in the middle scale. Just for an example here of some interview responses that and how they might have been classified. If a student kind of answers straight up that they're not interested, as in the first example here, then that is an obvious 0 answer or a no answer for us. And if the student simply said that they enjoyed the content that week, then that's an obvious yes answer to whether they had enjoyed the content. Now diving into our results, we can see some plots here. These are the first 4 plots. There are 4 more plots kind of categorizing all 8 of those questions that I mentioned earlier. we can see that there's a naming convention started here that is like SE1 for self-efficacy 1. And then it goes on SE2, SE3, and then we'll have engagement 1 for the first engagement question. And then there's 4 more engagement questions on the following slide here. As you can see, there's a general trend upwards for both self-efficacy and engagement as the course goes on, but there are some interesting spikes that we can observe visually, such as in interview week 3 and 5, we can see that there might be larger engagement or self-efficacy in some of these plots, and 4 and 6 see a slight decline in engagement and self-efficacy. This trend continues on the following slide here with some similar actions. Important to note that engagement question 4 is framed kind of the opposite. So it's whether the course had been too challenging. So a larger response involves less engagement, which is why there is a peak at interview 4 instead of a lower point as in the other graphs. But a lot of this kind of follows a similar trend, but might be kind of hard to notice visually. So we decided to also include the Spearman's correlation between the different questions to have a more numerical, much more easy to dissect view of how the questions were answered. So here's following the same naming convention as before with the SE1 through 3 and E1 through 5. And I've highlighted the responses that are 0.3 or higher to show some moderate correlation or more. So just diving into a couple of these here's the correlation between SE2 and E1, which were I feel interested in the course materials and have you been enjoying class, which might lead us to believe that feeling interested in the course materials was correlated to the student enjoying class. We also have, for example, feeling capable of success in the course was correlated to the student enjoying class, and feeling proud of their accomplishments in the course was correlated to the student feeling that they had learned new skills. Summarizing all of those kind of results as correlations here, we have that the belief in the ability to do well in the course was correlated to students feeling interested in the course materials. Belief in the ability to do well in the course was correlated to students enjoying class. Feeling interested in the course materials were correlated to students enjoying class. Feeling proud of their accomplishments was correlated to students feeling that they had learned new skills. Enjoying class was correlated to students finding the course topics interesting. And enjoying class was correlated to students finding that they had learned new skills. Now to discuss those results, we found that there were 2 major key findings that we wanted to focus in on. Students who reported higher levels of engagement with the course material often had a matching boost in their beliefs of self-efficacy. So we found that positive experiences throughout the semester, such as enjoying class and finding course topics interesting, were also correlated with a stronger sense of some aspects of self-efficacy. And this is important because self-efficacy has been shown in previous research to have a potential link to student success in the course. And it's kind of a difficult concept for instructors to really lock down and how to focus in on and promote, because it's this overarching feeling of the students. But if there is this correlation between self-efficacy and engagement, then it just goes to show that we can focus in on that day-to-day engagement in order to also promote that overarching self-efficacy and potentially that success of the student in the course. So all of that goes to show that targeting disengagement is equally as important in potentially as targeting losses in self-efficacy if they're correlated. So we also found that students reported disengagement when encountering challenging concepts that lacked clear structure and reinforcement. So the course topics that students found to be the most difficult were involving subjects that they likely had never seen before, such as designing and using data types, which is something that doesn't really come up outside of computer science for a lot of these younger students. As well as key findings, we also wanted to highlight some key contributions that this study can help kind of give to the research community. Overall, it can give an explanation of how to include the experience sampling method in computer science education context and a methodology for future research. It can go to help people develop engagement and self-efficacy questionnaires in this context as well. It can be a starting point for further research on the relationship between engagement and self-efficacy in this context. And it also can inform decisions in curriculum design around promoting student engagement. There are some limitations and recommendations, as with all research, that we can provide. So we had a relatively small sample size of undergraduate students who answered the interviews, and they also had a constrained number of interviews per student. which can definitely limit our data collection and the amount of data that we had. Participants were all international students, so potentially expanding this beyond just international students could help generalize the results. Some interview responses were definitely brief, which limited the depth of the data analysis. And the data that was collected was done so during a faster paced summer term, as I mentioned. So that summer term might have been more intense and difficult. So it might be more generalizable if someone can conduct the data or the research study in a regular term. So these are just the references I used throughout the slides, and there's more references in the actual paper itself. But thanks for these different references that helped guide our study. And thank you all for listening. I've included a small recap on the screen for when there's questions here, so people can kind of remember some of the key points. And that is it for me. Thank you.
There's definitely clapping in the room. Again, we will take until 4:50 or 10 to the hour in Portugal to have small group discussions, and then we'll come back to ask questions of the speakers. No, it's fine. Don't worry. Okay. Again, I'm interrupting small group discussions in the room, which is a good sign. What questions do we have for our speaker?
Hi. At the beginning, you said that the course is following how to design programs, but then the first week of the course mentions Python and functions. So am I not getting something? Is this an HTTP style but in Python? Or is it just Python and then HTTP in Racket or Pirate? What's going on?
Yeah, I'll let the course, yeah, for sure.
Yeah, thank you. That's a great question. Our intro programming course for majors is in Racket and fully following the How to Design Programs curriculum. This one follows the same inspiration with systematic program design, but in Python. Does that answer your question?
Yes, I'm getting a nod. Great. Other questions?
Okay, so if you're doing a how to design programs based Python course, could disengagement be caused by lack of a textbook?
I suppose it's possible. I don't think any students mentioned that. Most of our courses actually at UBC in computer science for first year, and at least one of our second year courses, the software construction course, don't use a textbook. I don't have any data to back it up, but we don't typically get complaints. We do have kind of homegrown reading material for them and video material support as well.
Okay, other questions?
So one question that came up at our table was, you looked at the correlation between engagement and self-efficacy. Did you also try to correlate these two things with the actual contents, like whatever happened in that week, what concepts or what parts of your content was covered, so that you could say this was one topic in programming that was particularly, I don't know, negative for self-efficacy or that boosted engagement?
Yeah, we kind of did. So as I was kind of mentioning in the study there, so the interviews kind of lined up with certain topics in the course. And a lot of the times in those interviews that were associated with a certain topic, the student would talk about whether that week that topic had caused disengagement or whether they enjoyed it or things like that. And that kind of qualitative data is explored more in the paper a bit. So there's a list of some of the topics that the students enjoyed and didn't enjoy, and that they engaged with and didn't engage with. But there also was some students who didn't give very large responses and didn't include specifics like that. So we kind of did what we could with what was available to us. But yeah, that is included in the paper as well.
Additional questions? I did have a question. My group had a question. It was a lot of things about implementation, right? Further implementation of this idea. So one aspect is whether you could include, rather than interviews, more self-reflection. So something that might be part of the course itself, right? As a graded element or something where you would collect feedback from the course as a whole, rather than just a small subset of opt-in students.
Yeah, so that self-reflection kind of after the fact is a common thing in a lot of computer science education research that's kind of existed already in the past. In other disciplines and other kind of educational areas, it's kind of been shown that a lot of the times whenever students kind of go for a retrospective after the fact, it's a lot less or potentially can be less honest and a lot maybe they forget things or they care a bit less. But whenever you kind of catch them in the heat of the moment, in some kind of event-based experience sampling, where they kind of just interacted with the course content. A lot of the times they'll have more to say or more specifics to say, and they care more about it because the student can be frustrated or happy, or you can really kind of capture that emotion of the student as they're experiencing it. So that's kind of been the idea in other disciplines. The experience sampling method versus retrospective interviews or reflections hasn't been explored a ton in computer science education. It's been explored more in other areas. So that's kind of one of the reasons why we chose to do it, is to kind of introduce this to computer science education and maybe spark further research that involves it in order to kind of have that contrast between retrospective reflections as well.
Thanks, that's a great answer to my question. Any other questions? Okay, let's thank our speaker. You can hear the claps from many miles away. Excellent. And so now maybe we'll take a quick 5 minutes and then we'll come back together at 5 p.m. to do just a half-hour discussion, retrospective, small group discussion. We'll say goodbye to our virtual participants and say thanks again for our last paper.